MAR organizing team, I would like to welcome you all to this workshop on multimodal algorithmic reasoning. And so the goal of this workshop is to understand the recent progress in AI from the perspective of say, a slightly theoretical side, for example, using neural algorithmic reasoning, or from the architectural point of view, using like multimodal large language models, and as well as interpret this progress in terms of how humans understand or how human intelligence works. For example, using the cognitive models of intelligence. And so the idea of this workshop is to bring these different perspectives and kind of try to understand in a holistic manner where we are and what are the steps ahead towards finding the missing rungs in the ladder of intelligence. And so we have a pretty packed program today, and we have 5 keynotes, 30 minutes each, with 3 oral sessions, 3 oral papers selected from the bunch of papers we received. And so all these keynotes are segregated into these different themes like neural algorithmic reasoning, large language models, and the cognitive models of intelligence. And as this is the same for the oral papers as well. And we have some best paper awards, and we were also conducting a Smart 101 challenge as part of this workshop. So we'll have awards for that. And then there will be a poster session that will be in the Arch building. And that's from 11:45 to 12:15. So without further delay, since we have a very packed program, I'll start with the keynote. So it's my pleasure to welcome Peter Velikcovich for this first keynote. So Peter has been doing a lot of amazing work in the area of neural algorithmic reasoning. He's a staff research scientist at Google DeepMind and is also affiliated with the University of Cambridge. And maybe if you have worked with geometric deep learning, for example, graph neural networks, his name is well known. He is an inventor of graph attention networks, as well as the graph deep informatics. And he has been recently doing a lot of amazing work in this algorithmic reasoning side of things with graph neural networks. So I'd like to welcome him for the first keynote and give him an applause for starting his talk. Thank you.
You need to allow me to unmute myself. Yes, just let me know when you've done that, and I'll share my slides in the meantime. Okay. And you'll need to unshare your screen so I can share mine. Yes. Cool. Okay, and right. So you should let me know if this works on your side. Perfect. All right. Thank you, everyone, for coming over so early in the morning to listen to this first session that I am giving today on embracing multimodality in algorithmic reasoning. My name is Peter Velikcovich. I'm a staff researcher at Google DeepMind and affiliate lecturer at the University of Cambridge. And it is my great pleasure to be here. This is actually my very first CVPR, and I'm having a fantastic time so far. So what we're going to be talking about today, just to sort of prime you and to kind of put you in the right frame of mind, what are the kinds of arguments I'm going to be making. We're going to be talking about classical computation. And when I say classical computation, I want you to think about the kinds of things you might typically encounter in an undergraduate course in computer science. So things like sorting, searching, pathfinding, clever ways to organize information efficiently, and so on and so forth. Of course, because we are in a deep learning context, we are going to talk also about how to take that computation and capture it with neural networks. And further on, thanks to the theme of the workshop today, we will also talk about multimodality. So how can we represent this data in various forms and have those forms interacting with each other to hopefully achieve something that our base models are on their own unimodally not capable of doing. So hopefully this will be of interest to broad areas of this audience. I promise you there will be also popular computer vision language models references throughout this talk as well. So it should be interesting to the broader CVPR community. Now, before I dive into the contents of the talk itself, I'd like to just take a moment to reflect on how we got exactly where we are. I've actually I've searched for the string neural algorithmic reasoning for all prior works just to make sure that my claim here is correct. And I actually haven't been able to find an earlier mention of the words neural algorithmic reasoning in research before October 2020, when I co-authored this excellent paper. So really, this was my attempt at organizing the various bits of work that were happening in the area at the time, broadly trying to fit computations into neural networks. And this was the first time we used this term when nobody else was using it. Sometime later, we wrote up this position paper on neural algorithmic reasoning. I would say a lot of the claims that we make in this paper are no longer correct, but I think in spirit, it is still something that's very useful as a guiding light. And yeah, it started from there, and I've been just blown away by how many different works have then taken this idea, this concept, and even squeeze it in their titles, and then these papers landed in top-tier conferences. These are just a handful of references, really, if after this talk you want to read a bit more about what people have been doing over the years and how it has gradually accelerated as well. So this is 2023 and 2024. You can see, once again, neural algorithmic reasoning features in a lot of titles, and people are generally doing some really interesting stuff with this idea. And this now led us to both a full-on tutorial that was at the Log conference a few years back, and also now we have full-fledged algorithmic reasoning workshops. And I just like to start by thanking the organizers for giving me the honor to present one of the keynotes at this workshop. I think it's a really fitting way to see that this term that I use to sort of organize information has landed pretty much in the spotlight. Now that acknowledgement is out of the way, I want to tell you a little bit about where I'm coming from, because the word reasoning, as you probably all know very well, is a super loaded term. Like, if you ask 100 different people, what does reasoning mean to you? They will probably tell you 100 different things. So I felt like it would be very useful for me to just be straight with the audience at the very beginning and tell you what it is that I want. When I say reasoning, what is the thing that I want to achieve, okay? And what I want is robust reasoning in neural nets. Now, let's make very clear what I mean by this, or specifically, what does it mean operationally for my team at Google DeepMind? So we've actually had many months of debates over this internally as well. Like, what is it actually that we want to achieve if we're working on a reasoning effort? This is roughly what we've arrived at. And I'm very keen to discuss any of these points with you later on after the talk as well. I'll be sticking around for the whole day. So for us, reasoning means a robust procedure for solving instances of problems, okay? This is really the fundamentals of what it is. The word robust is the important one. So notice I haven't said anything about accuracy. People sometimes, when they want reasoning, they want 100% accuracy. I don't think it's necessary to have 100% accuracy to have reasoning. Humans, we are, I believe, a good example of reasoning systems, and we are not always accurate, as you might know, right? In fact, one very good example of how human reasoning is not always accurate is the fact that it took me twice as long to find the conference venue yesterday than Google said I would need, because I was stuck in a loop somewhere, right? So human reasoning is often approximate, doesn't always get us where we want to be in the optimal way, but I would still count it as reasoning. And also, you might then say, depending on which camp you come from, that reasoning must involve explicit symbols, and you must explicitly explain every single step of what you're doing in a way that humans can interpret. I also am not explicitly requiring this. I think it's useful for interpretability if you have access to explicit symbols. But if I have a really potent, robust system that does all of its reasoning inside high-dimensional spaces, I will also allow this as reasoning. Some people might disagree with this, but this is the operational definition we're going for. But the key important thing, so it's not accuracy, it's not being symbolic, it needs to behave consistently or at least predictably across all problem instances that we care about. And what this really means is we care about out-of-distribution generalization. This is really the key mission that my team is trying to attack. And maybe a good way to put it in layman's terms is, if you want to build a model that truly captures and understands the concept of multiplication, for example, and you'll see why I'm giving multiplication as an example in a second, it should work equally well on all instances of multiplication problems, or at least tell you roughly how much it's going to be wrong if it's an instance that it doesn't, that it cannot deal with, right? And you'll see later on in this talk, we have even simpler things than multiplication that these models will tend to struggle at. But there's a very specific reason I'm starting out with multiplication. You might have seen papers and results like these before. You know, nowadays, the frontier models of use in deep learning are these decoder-only transformers, and they have hundreds of billions of parameters. Ergo, they compute hundreds of billions of multiplications just to generate a single token. But if I ask them to multiply 3 by 3 digit numbers, they cannot do this correctly. So here you have the accuracy of prompting a language model to multiply 2 numbers of different sizes. This here is with Gemini Ultra, which is one of Google DeepMind's frontier models. And you can see already 3 by 3 multiplication becomes really, really painfully bad, about 37% accuracy. Things obviously get worse as you increase the sizes. And just in case you were wondering, is this something specifically bad about Gemini? No, it's not. There are equally many papers that show the same effects happening with GPT-4. So this is not something that's like dependent on one specific LLM architecture versus another. It's a problem all of these frontier models have. Okay. And another thing that I think is quite important and will be important later on when we discuss certain possible solutions to these problems is we don't just want to solve it in a way that theoretically allows reasoning, and that's great. We also want to build something practical. So any solution that we explore should in principle be easily scalable to hundreds of billions of parameters so that one day it can actually land in some of these frontier systems effectively. All right, so this is what the aim for us is, and I hope it sets a good framework for the remainder of this talk. Now, you might ask, why bother with this, right? Like multiplication, or why bother with out of distribution? I often talk to people who are representatives of the scaling camp, and they will typically tell me one of two things. The first one is just gather more data. Out of distribution is not a problem if you have the right data for the problem, right? However, I think we've known this for a while now. Maybe these papers are not that familiar nowadays, but they have been quite influential and have been spotlights at top conferences previously that give this very simple geometric arguments for why no matter how good data you build, you cannot really generalize outside of that training data unless you do something really special to your architecture or your problem. This paper from Keolu Shu and others from MIT that was published directly in 2021 gives, in my opinion, the most beautiful one-line argument for this. And that is, if you take a ReLU MLP, which is a standard universal approximator network, it's a piecewise linear function. So when you escape the support of the training set, it has to become linear, right? So generalization is impossible if your target function is not linear, because eventually you're going to hit that linear regime. And what they've done in this paper is not just that observation. Arguably, that observation is quite obvious in retrospect. They've proved that the convergence rate to this linear regime is super, super fast. So the moment you escape your training set a little bit, and you can see this in a few examples in different dimensions, the model very quickly goes to predicting a linear function. And at that point, you cannot extrapolate, even if you wanted to. Of course, this result only holds for ReLU MLPs. Nowadays, we use different activation functions, but there are extensions that take this argument in the realm of causality or category theory, and I invite you to read these if you're interested to know more. The second thing that the scaling camp might say, and I will have a very concrete answer to this later in the talk, is just let your model call a tool or write code. We know how to multiply with calculators. Let your model call a calculator, right? Well, okay, sure. This does fix the problem, at least in theory. And research in this space was done for many years in the neurosymbolic community. Works like Toolformers have brought it back into the spotlight. The general idea is you use your neural network to predict inputs for a calculator or an algorithm or a code interpreter, and then that predicts the outputs you care about. This will not have out-of-distribution issues by definition, but arguably, I think it's admitting defeat before even starting. I'm not saying we shouldn't use tools, by the way. I think tools are going to be a really important part of generally intelligent systems of the future. I'm just saying we shouldn't just stick tools onto what we have right now and call it a day. I think we need to get better at our base models as well, because if you just stick a tool on top of it, you're acknowledging your network cannot do this, and you're committing yourself fully to any errors that the tool might propagate from what the model is predicting. And also, we'll mention later, doing it in this way introduces a lot of funky bottlenecks, which makes it brittle, hard to compose, and might require a lot of effort. So my conclusion from all of this is very likely we need to do something about the base model architecture to capture computation better. It's not going to be enough to gather more data. It's not going to be enough to stick tools on top of it. Now, once hopefully we agree that this can be a good avenue to push our research in, let's think a bit about how can we even evaluate whether a model can learn to generalize out of distributions. So let's think about what we need to support this kind of evaluation. We need some tasks for which we can generate outputs reliably, so it must give us correct answers even when we escape some reasonable problem sizes. It must be so efficiently, so we can generate data on the fly or pre-generate useful data sets. And it must be done for any distribution of interest which is valid, right? I argue that these 3 points, by definition, I've just described to you a polynomial time algorithm. Like, it's a tractable procedure that allows you to generate outputs for any input you care about, right? unless it's a problem for which you can easily scale human labeling, which might exist, but it's certainly not as easy as this. So basically what we need is algorithms, polynomial time algorithms. And when I say that, I mean the data of the form that you can see under the slide here. For insertion sort, for example, this is a standard polynomial time algorithm for sorting a sequence of numbers. And you can see gradually it starts with a list 5, 2, 4, 3, 1, and step by step it inserts one element at a time in its correct place. And at the end, you'll end up with a sorted list 1, 2, 3, 4, 5, right? And we have taken inspiration from this way back in 2020, and we worked on it for 2 years to try to create a unified benchmark which allows you to battle test your models out of distribution over a lot of polynomial time algorithms. And what we've developed is based on this textbook, which I believe should be familiar to many of you in the audience. It's the standard textbook for undergraduate degree courses in computer science. The CLRS textbook, as we call it, by the initials of the last names of its authors, Corman, Leiserson, Westenstein. And specifically, we've read through this entire book. We found that there's about 90 algorithms of interest in there. We've picked out a careful selection of 30, spanning a variety of possible reasoning skills you might want your model to exhibit, spanning sorting, searching, pathfinding, dynamic programming, string matching, and even geometric algorithms. So there's a lot of different skills that you can learn there. And we have released this publicly, as well as in the form of a companion paper published at ICML. One thing that's really important is because it relies on polynomial time algorithms, it's not just a single static data set. It's a data set and baseline generator. So you can easily add new tasks to this, change the input distributions for training and test, do whatever you want. The library will take care of both sampling the data, batching the data, creating models for you, and launching training runs. So you can really kind of just launch off a new task or modify a tiny bit on the processor network architecture and get results immediately. This is the reason why building this benchmark took 2 years. There was a lot of things we needed to put together, even though in principle, the ideas were quite simple. So you can read our companion paper if you want to know more. And also we have a fully open source implementation at GitHub that you can use to start generating this data today if you want to play with it. And what have we done with these models? We were interested in training generalist models that are capable of reasoning. And as you can see from these representations, one very nice unifying structure that can be used to reason about all of these problems is the graph. So graphs are basically a very nice way to reason about discrete data in models. And what we wanted to build is a single model capable of executing all of these different algorithms. So think about a model that can do sorting, pathfinding, convex hull finding, all in the same core architecture. Of course, the problem we have is that data has different shapes. So we needed to have separate encoders and decoders, but we could share the central part of the computation. And it turns out when you train a model like this, you get something which is actually quite generic and powerful. It's a work that we published at Log a few years ago. And here you can see the performances of our single multitask trained model on executing on 4 times bigger inputs, so out of distribution, against single task specialists trained on each individual task. And for all intents and purposes, on some tasks it's better, on some tasks it's worse. But on average, we basically have this one generalist that's roughly equally potent as individual specialists. So it's a pretty good result for the capability of building such systems. Obviously, we have more to go to make these curves go up. But in principle, it generalizes to 4 times larger graphs. Now, nowadays, obviously, people still work a lot with GNNs, but there's a lot of interest happening in the language space. And we felt it would be a great idea to try to build CLRS30 into the LLM age. And by the way, many reasoning papers on language models build their own synthetic algorithmic data sets, usually for addition or multiplication or things like that. So modifying our benchmark to suit language models also unifies a lot of these previous papers. So it's another kind of useful addition. So we created a language version of CLRS, which we call CLRS text. And it's still in the same GitHub. You just need to add a little bit of extra path to reach the folder where the text files are, or text file generators. This was a great collaboration with Sean, Tom, and Avi from Maryland. And this is basically what the data will look like. So now you have textual versions of those graph traces I showed you before. The model is prompted with the part in green, and it has to predict the trace in blue, which shows you how gradually the array gets sorted as it does insertion sort. And it's evaluated on the final part in red after the pipe character. So you say that an output is correct if you have an exact string match that gives you correctness on the final thing you produce. Now, another great part about this benchmark is that, remember how in the graph version, we needed to have a separate encoder and decoder for every modality? Now that everything is in text, we can have just one LLM trained on everything. So let's see how well that does. It actually doesn't really do that well. So these are some of the results. There's 30 algorithms in CLRS text. You can see the full plots in our paper. But these are some of the results we get for various, both few-shot prompted state-of-the-art models and fine-tuned smaller models. So first thing that you can observe, the curve in green is Gemini 1.5 Flash, which is a really fast frontier level model distilled from Gemini 1.5 Pro. We've two-shot prompted it on these things, so it's aware of the formatting. And you can see it generally doesn't perform that well for most of these algorithms. There is a huge gap that you can unlock if you fine-tune on some of these sequences. So even though these models have been exposed to a wealth of algorithmic traces on the internet, they clearly haven't learned to prioritize that information, and they cannot really robustly do it. Additionally, even in the realm of fine-tuned models, so here we use the Gemma 2 billion model, which is a relatively small model, but you can efficiently fine-tune it on these sequences. You can see that even in the realm of fine-tuned models, you can have huge uptakes. This is like 60% improvements for certain sizes, if you add some small tricks like better position embeddings. Position embeddings are an easy way to lose out of distribution performance if you do it badly. Here, just by adding randomized position embeddings, we get a much better performance on some of these algorithms. And that's the gap between the blue and the orange model. But another thing you might notice, the red dots you might be able to see on the slide are the sizes of the problem we trained on. And you can see the moment we escape the largest size that the model is trained on, you have this sharp drop of about 60%, basically to zero accuracy, right? So there's a very big weakness out of distribution in these models that you can see on all the algorithms. I've just highlighted one, but it happens everywhere, right? So this is a big problem because at a first glance, it might seem quite surprising. GNNs easily generalize to 4 times bigger inputs. LLMs cannot generalize to +2 larger inputs very easily. Why is this? And we actually believe that the culprit is the autoregressive nature of large language models. Specifically, the fact that all paths that matter must cross through the final token, which predicts the next token for next token prediction. And what does this mean? This means that you can construct inputs for which these representations gradually collapse. I'm not sure why my images are not loading. Okay, hopefully they will load. Okay. This is a bit unfortunate because it's supposed to show you the things that we can do on these things. Okay, well, hopefully, there we go, the image is here. So first of all, you can easily construct a sequence of inputs for a language task where you make all the tokens the same and the last one is different. And you can gradually, as you increase the size of the problem, the representations of that final token will start to collapse. And eventually it will become smaller. The difference between 2 different sequences, the embeddings of the last token will become smaller than machine precision, which means the model will be unable to reason about those 2 things differently, aside from effects of random sampling. And the second one, this is very nicely explained as a picture. Because you have this causal masking, which allows a token only to send into the future, tokens at the earlier part of the sequence have way more paths to the final token bottleneck than the ones later in the sequence. And you can easily end up with over-squashing of information where the earlier tokens are in a much better position than the later tokens. And this is an inherent bias of the computational graph of the system. And by the way, because of this, they probably struggle with rudimentary tasks like counting and copying. And these bars here are just the errors. So how big is the error when you ask the model to just sum 1 + 1 + 1 + 1 + 1 of a certain number of ones? The errors just grow, and adding chain of thought does not help. And if you look at the error analysis, it's not just that the model slightly gets it wrong. It illustrates the model clearly has no idea what it's doing. This is the distribution of answers that Gemini 1.5 gives when prompted to do these various counting tasks. It tends to really like the number 100. It will just say 100 when the number is big enough and not really try to do anything else, right? So clearly it hasn't learned the algorithm for counting. And by the way, you may say these kinds of problems are easily solvable with tools, but good luck using a tool if you can't even copy your input into the tool, right? Now, what's the culprit? This is not something that's inherently bad about transformers. It's only about the fact that their decoders are trained with this causal mask objective, which exposes a bottleneck in the final token. And repetitions make things worse. So if you add some simple tricks like inserting commas between repeated tokens, as you might do in these finance data, this actually improves a little bit the representational differences. And if you want to know more about it, we have this paper on transformers need glasses, which elaborates on this further. But arguably, this is just a small mitigation strategy. It's not a panacea. Ideally, you want communication between tokens to be unrestricted, but this is harmful to scale. We have causal masks to allow us to train these models easily at scale. So what instead? We had a non-autoregressive model that we plugged together with the autoregressive model in a multimodal fashion. And that leads us to the transnar architecture. So the way it works, and we actually published this at the workshop here today, it will be presented. We have basically a GNN that's trained on this graph data, as we described before, and can generalize to 4 times bigger graphs. And we let our LLM cross-attend to the embeddings of the GNN to extract that information that comes from the non-autoregressive pipeline. And hopefully this makes things easier. And this is what it looks like. And I promise there will be a famous vision language model mentioned here. So you have your transformer part that works on the tokens. You have your GNN part that works on the graph. And then because these two have very compatible representations, you can just do standard flamingo-style cross-attention to map the embeddings of the nodes of the graph into the embeddings of the tokens of the transformer. And just by doing this one simple trick, you get huge improvements on out-of-distribution reasoning on CLRS text. So some of these improvements for different categories of algorithms are well over 40% or even 60%. I believe in language model literature, when you have an improvement of 20 or more percent, you tend to call it emerging capabilities, I believe, something like that. Yeah. If you want to know more about transnar, this is a paper that was a great work from Wilfred as the first author and many others from my team at DeepMind. Unfortunately, Wilfred could not be here with us today because of visa issues, but I will be presenting. I've brought the poster today, and if you're sticking around for the poster session, I'd be very happy to talk to you more about this. So one closing remark I want to make is that transnar is mainly a proof of concept. It shows that if you include this multimodal information with non-autoregression, it helps you bring benefits in reasoning tasks. However, you cannot easily use such a model out of the box if you don't have a graph that you can use as a second modality. And we hope our study motivates some future research into fixing this problem. One very simple, promising avenue we're currently exploring is distillation, right? Once you train a multimodal transformer, can you then distill its logics into a unimodal transformer, which only looks at the sequences? We explore various trade-offs of distillation versus next token prediction, and we're actually able to train a competitive unimodal distilled model at 0.25 loss factor, which actually beats the baseline, which is the model in blue. That's the base transformer in out-of-distribution reasoning. It doesn't work everywhere. It doesn't work everywhere with equal performance, but we at least have this preliminary result to show that it is in principle possible. So in conclusion, reasoning out of distribution, I think, is going to be really important, especially if we want to do science with language models or to do any kind of robust reasoning. And I believe in the computer vision community, you come across these kinds of problems all the time for self-driving and similar problems, right? And our frontier-based models are fundamentally bottlenecked. The very computation graph of the transformer exposes a bottleneck in the last token, which means information is not treated equally and can very easily get lost. If you want to read more about it, the paper from Federico Barbero and others is a great reference. One way out of this conundrum, there's many possible ways out, but this one is particularly, okay, this. Okay, cool. So one possible way out of this conundrum, there's many possible ways, but the one that we have explored in this work is to embrace non-autoregression. And one very easy way to introduce non-autoregression without breaking the scalability of the transformer is to embrace multimodality. Train a non-autoregressive model on the non-autoregressive data, and then let the transformer use its embeddings. This leads us to transnar from Wilfred Bonsi and others, which we will be presenting at the poster session later today. And lastly, if you want to try other ideas or improve the non-autoregressive idea and have a good benchmark to evaluate out-of-distribution language capabilities with access to the graph modality as well, we now have that as well. We have the CLRS text benchmark that is publicly available on GitHub, and we're very happy to help you use it if you want to try it out for yourselves. This is great work from Larissa Markieva, Sean McLeish, Borhai Bars, and many others at DeepMind in Maryland. That's my last slide. Thank you very much for listening, and happy to take questions.
We have time for 2 or 3 questions. So there is no microphone that we can bring over there, so you probably need to speak louder. Sorry.
Excellent talk. I would say if you could comment on the sort of computational complexity of transformers. So we have a sort of quadratic complex in terms of input, and for many algorithms, you really would be one not only sublinear, but not only quadratic but also sublinear. complexity that you don't even need your whole input in order.
Yeah. So
maybe you have to repeat the
question. I'll repeat the question. So the question, if I understood correctly, is about commenting on the computational complexity of the algorithms and how it relates to what the transformer is doing. This is a very important point. Basically, many algorithms, as mentioned, especially when you parallelize, the computations are not just subquadratic but sublinear. So a lot of the computations that the transformer is doing might be redundant. However, even though there's lots of redundancy, we've shown here, so the task that I showed earlier, like counting and copying, is literally pluck out one character out of a whole sequence, not even copy the whole thing, very clearly sublinear. However, the model struggles even with that. So I would say at this point, it's less about computation complexity and more about allowing the information to travel through the transformer in the most effective way. But yes, especially when we talk about generalizing over longer sequences, you're probably going to also want some recurrence in there. Currently, the transformers have a fixed number of layers, follow the base architecture as before. This will obviously break eventually, but on the sizes we have, it wouldn't. But it's another thing to think about once we sort out this initial problem. Yeah. There's a question there. So this is a great question. I'll just repeat it. It's talk about how to interpret what these models are doing beyond just looking at out-of-distribution performance. So I'll try to quickly sweep through to find another paper I want to share here. But one thing I can say is one of the things we do in the Transcend AR paper, which I'll talk about during the poster session, is we can also look at not just at the accuracy, but also at the shape score, for example, and the parse score. So is the model capable of following the format of the problem? And is it capable of predicting the arrays of the right size? So one thing we discovered there, it's very rudimentary, but it's already a starting point. The ways in which these baseline transformers fail often is that out of distribution, they fail to even predict the correct shape of the array because they're not used to something of that particular size. And having randomized position embeddings or this non-autoregressive training helps with that. So that's one thing we discovered. Another paper, which is really beautiful that you can do, especially with the GNNs, is to analyze how the representations in the high dimensional space move as you solve the problem. And this paper here from Vladimir Mirjanic, latent space representations of NARs, basically puts the high-dimensional embeddings of these GNNs into PCA space, so two-dimensional, three-dimensional. And he has these really beautiful plots on how those embeddings move through time as the model learns to solve things. And actually looking at them this way helped him to fix many of the architectural problems with these systems. So those are two things that immediately come to mind. Yeah. Another question in the back? Yeah.
So if that's still the case, are we still looking at bottlenecking? How would you diagnose that versus the oversquashing?
Right. That's a great question. So I would say both are problems that are kind of tangential. So here you can see, just to highlight it again, if you add randomized position embeddings, it can give you a lot of boost. The main problem is that the position embeddings, at least the popular ones, are always the same in every position, which means that if you give the model a bigger array at test time, it will see combinations of position embeddings it never saw, and it can easily overfit to the sizes you're giving it. Randomized position embeddings are a simple way to break this problem by just randomizing the positions that you give to the system as long as they're in sorted order. That's a really easy thing to do. Nowadays, there's a lot more great suggestions like fire embeddings and recently abacus embeddings, which are even more fine-tuned to like figuring out the different positions of operands and stuff like that. I think position embeddings are going to be a really important area for research here, and they're arguably the easiest way you can see gains. Like make a marginal change in the code, run off your same training script, see a big improvement in the curve. So at least in the short term, that's going to be the easiest. Non-autoregression is already a bit harder, right? And how does it compare to oversquashing? I would say they're two complementary things. So position embeddings kind of are there to help you, hopefully, if you do that right, generalize better to different sizes from a positional perspective so you can easily index into different places. Oversquashing is a problem that just means that things that are earlier in your array are going to have a much easier time propagating information than things that are later. Couple that with the fact that a model learns a recency bias just because the last few characters are always most important for next token prediction in many cases. The tokens in the middle are very painfully understaffed, and this results often in the U-shaped performance you see in retrieval, right? So I would say you can fix P's, but you still haven't fixed the oversquashing problem. For that, you might need to, well, one direct thing you can do is change the computation graph structure of these models. Yeah.
So unfortunately, we are out of time. So maybe if you have more questions, feel free to meet Petar later.
Yeah.
So thank you so much, Petar, again. Let's have a
I can't hear you, by the way.
Dr. Bing, can you hear me?
Yeah, I can hear you now. Thank you.
Hear through this microphone, laptop. Yeah, you can talk through that, but she will hear through this.
So that's okay. Let's start. Ladies and gentlemen, it is my great honor to introduce Dr. Chelsea Finn, an assistant professor in computer science and electrical engineering at Stanford University, and a co-founder of Physical Intelligence. She has her research interest is her research focuses on enabling robots and other agents to develop broadly intelligent behaviors through learning and interaction. And she has made significant contributions in areas such as vision-based robotic manipulation, meta-learning for visual learning, and scaling robot learning to broad data sets. So today we are talking about AI reasoning and multimodal models. But how will this affect robotics? So let's hear from Dr. Chelsea Finn in her keynote on robotic reasoning with vision language models. And yeah, so let's start. But unfortunately, Dr. Finn cannot be here in person today. But let's welcome her virtually. Yeah, let's give her a warm welcome. Yeah.
Great. Thank you for the introduction. Hopefully the audio and video is all good. Really sad that I wasn't able to make it in person. I unfortunately caught COVID late last week and canceled my flights so that I wouldn't get everyone at CVPR sick. Cool. Is the audio all good? Cool. Okay. So I'll get started. I'm planning to talk about how robots can leverage foundation models for high-level planning and reasoning. And oh, a noob can't hear me. I think it's on the Seattle side. I'm not muted. Let me know if I should say anything to help test.
Yep. Can you can you speak, Chelsea?
Is this better?
You can
So you can hear?
Yes. Yes.
So should I start or?
Can people hear? Is it okay? Okay. Yeah, you can start. Thanks.
Okay. Great. Really sad I wasn't able to make it in person. I got COVID late last week, and so I had to cancel my trip to Seattle. There should be some time for questions at the end if anyone has questions. Yeah, and I'll get started. So I'm really interested in whether we can leverage foundation models for high-level planning and reasoning in robots. And specifically, I think this is really interesting because any sort of scenario where a robot might need to be accomplishing something over a long time horizon, it's important to be planning and reasoning at a high level rather than just making small adjustments to the robot's actions. Now, in some work a couple years ago, we looked at leveraging language models to help robots plan. As an example, we might prompt a language model saying, "I spilled my drink, can you help?" with the hope that the language model can help provide a list of potential things that the robot can do in order to help. And so an ideal planner would leverage the language model to kind of break this down into step-by-step things: to find a sponge, pick up the sponge, come to the person, put down the sponge, potentially also help them actually wipe up the spill and so forth. Now, unfortunately, if you, naively ask language models this sort of prompt, they'll suggest things like, "Do you want me to find a cleaner? You could try using a vacuum cleaner." Or Fawn will actually say, "I'm sorry, I didn't mean to spill it," which isn't exactly the kind of useful planning or reasoning that we want from these models. And so naively applying foundation models for high-level planning and reasoning can sometimes be helpful, but it's challenging to get them to be most effective for integrating with robots, because they need to have a lot of understanding of the environment and of the robot's capabilities. And so what I'm going to talk about today is how we can leverage foundation models, and specifically vision language models, with robots for better higher level reasoning. And we'll actually look at this both in the context of legged locomotion as well as manipulation. Cool. So let's start with some locomotion examples. And as like a kind of to set things up, we're going to prompt the vision language model with a language prompt to kind of give it some information about what the problem is, generally that is controlling a robot at a high level and so forth. And we're also going to give it images from the robot's egocentric viewpoint. And so these are images taken from an RGB camera mounted on the robot. And then from there, the goal is for the VLM to output a skill, one of a few different options that it has to walk, climb, crawl, turn left, turn right, or move backwards, as well as a magnitude, small, medium, or large for that skill. So this is like a fairly simple setup, and it has like some structured output of what it can do at a high level. And so it should be in some ways fairly straightforward for a vision language model to look at an image and predict a skill. But unfortunately, we find that naively prompting a vision language model to output the skill at each time step can struggle. And in particular, the vision language model can misinterpret the scene, or it can misinterpret what a skill might do or the robot's own capabilities. And it's also really easy for the robot to get stuck where the vision language model either isn't sure what to do, or it just repeatedly provides the same high-level action without making any progress. And so in this project, we kind of investigated and tried investigated kind of what VLMs do in different circumstances, and specifically how we can improve upon the naive application of VLMs to this problem. And there were two really key ingredients that we found to be really helpful for actually enabling robots to reason about the situation. And the first was to incorporate history. So instead of only looking at the current image of the robot, actually incorporating a number of previous images and previous high-level actions that was taken, And by feeding this history into the context, the robot should be able to identify if it's stuck and try a new strategy if it is indeed stuck. And the second thing that we found to be helpful is, in some ways, perhaps it's somewhat intuitive that it might be helpful because it's somewhat similar to chain of thought reasoning. But we found that it's quite helpful for the vision language model to actually not just output the what skill it should take at the current time step, but it should also output actually the skills that it should take multiple steps into the future. And we found that this actually substantially improved performance and helped the robot foresee if there was going to be a potential failure later down the line in its future. And so we refer to kind of the combination of these two things with the VLM as VLM predictive control, in the sense that this is actually quite analogous to model predictive control, where we're going to be planning multiple time steps into the future, except at a very high level in terms of high level actions the robot should take. And then each time step will also be kind of replanning to plan out a new sequence of actions and only taking the first skill in that sequence and executing that on the robot. A little bit more specifically, here's some examples of kind of an excerpt from the prompt that we used. The first was regarding history. So we prompt the VLM saying that the beginning of your response should use the state of the robot, including its current position and orientation, to reason through what progress the robot has made with your previous plan. And so this is kind of prompting it to think about both the current information as well as the previous information that's in the history and the context. And then with regard to thinking about multi-step plans, we prompt the VLM to describe a multi-step plan using the available actions specified above for completing the task and give reasons that the plan might fail. You should reconsider your previous multi-step plan of actions to take, keeping in mind the history of what actions you have selected and the progress in the scene. Now, if we actually kind of, for this example, and we actually look at the output of the VLM, we see that it's able to reason through and realize that the robot is facing the same piece of furniture and indicating that it should find a different approach. And then it chooses an approach that kind of instead turns to the left, walks and crawls, rather than simply trying to move forward into the piece of furniture again. Cool. So we're going to evaluate whether we can use vision language models as a high-level planner for legged robots. And the kind of setup that we're going to be looking at is, again, we're going to have like a low-level, essentially language condition controller, and a high-level, the high-level policy will be either VLM with history and with a multi-step plan, or without one of those two things, or simply a random high-level planner that randomly selects a skill to use. We designed 5 different settings for the robot to try to tackle, and the goal in all of them is to try to reach this red chew toy for the robot dog. And I should really emphasize that these are, well, first, if you look at this from kind of the third person point of view, it looks somewhat simple for the robot to navigate the situation, but the robot only receives egocentric images from the robot's camera as input, and it has to use that. That's the only information that it gets. And the second thing here is that it really needs to combine both really low-level skills like crawling and climbing over objects, as well as high-level reasoning over what it's tried before in order to successfully succeed in the situation, because there's lots of obstacles, including obstacles where it's required to crawl under something or where it's required to climb over something in order to succeed. Cool. So let's look at a few examples. So this is one of the first examples that we tried. And if you use a vision language model without history, the robot will, or the vision language model will keep on trying the same sort of approach over and over again, where it's trying to go forward. It does actually eventually turn left, but then gets stuck in a situation where it looks somewhat clear, but the right shoulder of the robot is stuck on the leg of this couch. And in contrast, by incorporating history, the robot is able to very quickly, it tries to go under the couch, realizes that that's not successful, backs out, and then eventually tries a new strategy to successfully get to the chew toy. Here's another example where the gap between these two things is too narrow for the robot to go through. And so it looks like it might be able to go through, but it's struggling, and without history, it doesn't realize that is not going to be able to go through the gap. And in contrast, by reasoning about the history of what it's tried before, the robot is able to navigate to the chew toy successfully. Now looking at some outdoor examples, this is another one without history. In this case, the robot is on this kind of somewhat unstable step. It's a little bit challenging to see, but there's this unstable piece of wood step right here. And it's not actually something that the robot is able to walk over using a walking skill. It kind of looks like it might be able to walk over it, but it can't. And by actually using history and then trying a new approach of climbing over it rather than walking over it, it's able to successfully kind of traverse the situation rather than getting stuck. Cool, a couple other scenarios. This is a scenario where the left side is showing using history, but not using multi-step planning. And it's not able to figure out a plan that eventually gets to the chew toy and eventually walks kind of out of the scene. And then in contrast, here we're able to figure out a plan that that is able to kind of navigate under the bench and to the toy. And lastly, one other example, again, the robot only sees these egocentric images that are right here. It's really easy to get stuck in the bushes and kind of repeatedly try a few different strategies. And without multi-step planning, it's not able to successfully kind of navigate the situation. But by doing so, it's able to navigate the situation more quickly here on the right. So those are some qualitative examples of the kind of scenarios that we put our robot through. Quantitatively, we compared these different methods, and not using history is shown in dark blue, not using multi-step planning is shown in the salmon color, and kind of the full approach is shown in this turquoise color. And we find that overall, we see a 20% or larger improvement across these metrics. This is looking at the average time to completion, the median time to completion, and the success rate. And we find that really both history and multi-step planning are really important for actually effectively using vision language models for these tasks. And especially, really both of them are really important. If you're going to pick one of them, using history is especially important and leads to higher performance than only using multi-step planning. Cool. And then one other thing that we tried is to see if we could actually improve the robot further by giving it in-context examples. And the idea here is that if the robot has seen the situation before, or seen similar situations before, and it understands the effects of what its skills do in different scenarios, then those kinds of examples of whether it succeeded or not at applying a skill in different scenarios should be really helpful for the robot when trying to solve the task again, or trying to solve a different task in a new scenario. And we found that indeed, actually, if you include these in-context examples, the robot can actually sort of do in-context reasoning and learning about what the effect that its skills have on the world. And we see kind of a 20% improvement in performance with these examples and a 50% reduction in time to completion. And in both of these two pretty challenging scenarios that the robot had never seen before, it was able to traverse them with 100% success rate with the in-context examples. Cool. So the takeaways here are that history and multi-step planning really greatly improve the adaptability of the robot to different scenarios. And this in turn improves the robot's resilience and performance. And you can sort of think of it both as like reasoning over time into the past and into the future. And together, that really improves the robot's ability to reason about how to address a scenario. This is sort of analogous to MPC, but at a really much higher level VLM planner rather than over low-level robot actions. There's also many open questions here. We used a fairly simple approach for kind of attaching language to locomotion policies, where we essentially took the controller actually that just comes with this robot and attached verbal tags to them. But there's a lot more that can be done there to try to ground language into low-level locomotion policies. And it's also clear that it might be challenging to describe different robot behaviors in language. And so thinking about ways to expand on the language abstraction while still getting the benefits of vision language models is a really interesting open question. Cool. So I talked a bit about locomotion and essentially like different ways in which we can affect the VLM's reasoning to improve it for these challenging locomotion scenarios. Now I would like to talk a little bit about manipulation, and I think that the same lessons hold for manipulation, but we found that actually applying VLMs out of the box is more challenging when we're in manipulation scenarios. And the setup here is we're going to be looking at really long horizon bimanual tasks, like putting all the objects into a bag or making trail mix. It's really expensive to collect data for this. And so using a vision language model or using some sort of high-level planner that might be able to reduce the amount of data we have to collect, it can be really helpful. So the problem setup here is we, at each time step, the robot will kind of look at the scene, will again have like a high-level planner that's outputting language and a low-level policy that's predicting actions based off of that. And then at a given time step, we may also have a person interject and change the instruction that the robot should take, the high-level instruction that the robot should follow at a given point in time. And ideally, we'd like this language correction data to both be able to improve the robot on the fly, as well as improve its performance through some sort of post-training procedure. And so we want to actually kind of be able to leverage high-level language supervision in these two different ways, both like literally at test time as you're running the robot, as well as for further improving the policy. So like I mentioned, we're going to have a hierarchical policy, and specifically the high-level policy will take as input RGB images and output language instructions. So you can think of this as a vision language model. We're not actually going to use a pre-trained vision language model for this because it was simpler to train something from scratch, but it's definitely something that we're excited to do in future work. And then separately, we have a low-level language condition policy that we're training with imitation learning. Now, the key insight that we had in this work, which is in some ways pretty simple, but I think quite neat, which is that if your low-level policy can follow a wide range of instructions, then you can actually just improve the overall system simply by improving the high-level policy. Essentially, by improving the high-level policy to be able to kind of provide language instructions that can compensate for inaccuracies in the low-level policy. And one thing that's really cool about that is that this means that you can actually improve the overall system only with language supervision without collecting further demonstrations. You can essentially update the language, the high-level policy, the output of this is language, so you can give it language annotations and labels to improve this high-level policy without actually having to collect any additional demonstrations with teleoperation. And so the method that we're going to be taking here essentially corresponds to Dagger on the high-level policy and freezing the low-level policy, if you're familiar with Dagger. If you're not familiar with Dagger, no worries. Essentially what we're doing is as the robot is executing a long horizon task, a human might intervene and correct the robot verbally with what it should do. These language corrections will override the high-level policy prediction as you're running the overall system. And then you can fine-tune this high-level policy on those interventions in order to say, in this situation, this is the correction that you should have provided to the low-level policy in order for it to succeed. Cool. So we have this frozen low-level policy, and then we're updating the high-level policy by supervising on these language corrections. We gave this system a fun name, Yell at Your Robot, or Yay Robot, because we're simply providing these verbal corrections to the robot. So we can look at, again, some kind of qualitative results. I think this is like really the coolest part to see in most robotics papers. The base policy is a language condition policy, and it's the kind of the full system of a language condition low-level policy and a higher level policy that outputs these instructions that are shown in yellow. And we see that it can make mistakes, and it fairly rarely issues corrective commands. And so if it's trying to pick up a Sharpie, for example, it might repeatedly fail and still be outputting this high-level pick up the Sharpie command. And then after fine-tuning with language corrections, we find that the policy is able to self-correct. So in this case, it fails at the insertion, and the high-level policy is actually telling it to move towards the camera, go higher, which is kind of correcting the behavior of trying to simply put it into the bag. We also find that it's able to self-correct for grasping, where the high-level policy tells itself to move to the right before picking up the tape holder, and then also to try a different strategy for putting the sponge in the bag. So right now it's kind of trying to kind of shove the sponge into the bag. It eventually releases the sponge and pushes it into the bag by poking it instead. And then overall, by using these language corrections and fine-tuning the policy on the language corrections, we see that the overall behavior is more successful at the full long horizon task. This task is pretty long, so I won't play the full video, but we can see that it's able to really kind of fully complete this task of putting the objects into the bag, which is in kind of robotics land a really, really challenging task because it requires kind of executing a lot of things in sequence involving objects that are really hard to model. Cool. And then the other thing that we can do is we can actually improve performance on the fly. And this is something that I think is actually really cool, which is that I'm going to pause the video right here. You can actually see that the robot's about to make a mistake here, where it looks like it's about to pour the peanuts on the other side of the bag because the scoop is not successful into the bag. And we can actually preempt this by verbally interjecting and telling the robot to stop. And sorry, let me play this again. So we're going to interject at that point, and the text on the top left will show how the person is interjecting. So they're going to say, move the arm to the left, go higher, and then move the scoop into the bag. And then the robot will continue autonomously. And we see that the person is able to kind of preempt the policy from failing and ultimately succeed at the task. One other thing that's cool is that after fine-tuning, we actually see that the policy doesn't just rely on the human corrections on the fly. It'll actually self-correct in the same way, where it was about to put the craisins on the other side of the bag, then it moves higher and successfully puts them into the bag. Cool. So those were some of the qualitative results. Quantitatively, again, we also see, in this case, a 20% gain in performance just from using verbal corrections, which is pretty cool. And it closes a lot of the gap between using kind of on-the-fly human corrections, which are kind of an oracle shown in this lighter orange color. Also worth mentioning that the low-level policies have a lot of room for improvement. The kind of overall average success rate is around 55%, which is a lot lower than 100%. And this can really just be explained by the room for improvement in these low-level policies. Cool. So the takeaways for this part is that you can now productively yell at your robot, and the robot can improve only from language feedback by fine-tuning the high-level instruction policy without requiring any demonstrations. Limitation here is that this relies on a really performant instruction following policy as a low-level policy, and improving this will, I think, really improve the ability for the high-level policy to succeed and really follow through on the kind of planning that it wants to do. Cool. Yeah, so that's it. I'd like to really acknowledge Annie, Alec, Andy, Govind, and Lucy, who led the works that I presented. And yeah, happy to take a question or two if there's time.
She cannot hear. Dr. Finn, can you hear us?
Yeah, I can
Can
hear
you hear
now.
us? Okay, awesome. Could you please?
Hi, Professor Finn. Thank you so much. My question was, like, I noticed that you asked the VLM prompts and for reasons that the plan might fail. And I was wondering, does this help the robot evaluate what went wrong and then react dynamically? Like, why do you ask it specifically why it might fail?
Yeah, that was not something that we like did detailed quantitative ablations on because the evaluations take quite a bit of time to run on the real robot. But we did kind of anecdotally find that asking it to think through the failures was helpful for it to improve performance.
Okay, I think we are out of time. So yeah, let's thank Dr. Finn again. Yeah. Okay, next we are going to have the oral paper presentations. So the MAR workshop has selected 3 outstanding papers from 3 subsections of the workshop for this session. And first, our first oral paper presentation is by Scott Murray on spatial representations in multimodal AI systems. And let's welcome Scott to the stage.
Yep. Thank you. My name is Scott Murray. I'm a professor in the Department of Psychology over at the University of Washington. My background is in visual cognitive neuroscience, so using brain imaging to understand the visual system. Recently, my research scientist and I, Bridget Leonard and I, have been looking at spatial representations in various multimodal AI systems. Today, I'm just going to be talking about GPT-4. Our approach is very similar to how we do experiments in humans. We start off with some observations, generate hypotheses, and then do experiments. One observation that's relevant for today is that even though GPT-4 is brilliant at coming up with a complex description for a really simple image like this, rich in all kinds of spatial understanding, like a person with a ball, a barrier, and a target. Sorry. Sorry about that. No problem. You good? You were here? Yeah. Okay, cool. Thanks. So even though it's great at this, we noticed that if we turn the image upside down and included the prompt imagine rotating this image upside down, what's going on? Does it recover any of that previous description? It does not. The description is very different. So it describes the upside down image as being a collection of geometric shapes, and its imagine rotated version of it still appearing as a collection of intriguing geometric shapes. So it was observations like this that made us wonder whether GPT-4 was even capable of transforming spatial representations. We know from the developmental and developmental psychology and neuroscience literature that there's really two broad domains in which to consider spatial transformations. One is in an egocentric reference frame. A classic example is mental rotation, and the other is an allocentric reference frame, a classic example being perspective taking. So we did a number of experiments in both of these domains. In terms of mental rotation, you have to be careful about how you do these experiments. So for example, if we give these two images to GPT-4 and ask for a comparison, it gives a nice long-winded description where at the end, it accurately concludes that these are two different views of the same room. Now, even though you and I might make or use mental rotation to do that comparison, GPT-4 might just be generating a long list of linguistic labels and comparing that list to come to that conclusion. So for our mental rotation experiments, we turn to classic stimuli from cognitive psychology that are more difficult to solve using linguistic labels. And using these stimuli, the experiments that we describe in our poster demonstrate that GPT-4 does not behave in a way that's consistent with mental rotation. In terms of allocentric reference frames, we also don't see evidence for spatial transformation. So if we go back to the room example, and now prompt with, if you walked into the room through the door, would the plant be to the left or to the right of you? For the image in panel A, GPT-4 is wrong 90% of the time. It responds left. It's basically just staying in terms of the image information or a viewer-centered reference frame. In panel B there, it's interesting because in terms of image information, the door and the plant perfectly line up, and appropriately or consistent with that, GPT-4 is answering left and right 50-50. So overall, we don't see any evidence for GPT-4 being capable of transforming spatial representations. One reason this might be the case is that language itself is just a cumbersome format to make spatial comparisons. So for example, with these two images of objects that have very different 3D configurations, superficially at the level of linguistic labels, they're kind of similar. They have, you know, 3 arms, one of them's long, one of them's short, etc. So it might not be surprising that GPT-4 had difficulty discriminating objects like this. Now, as a neuroscientist, I'm prone to make analogies to the brain. So our visual system is comprised of 2 visual processing streams, a ventral processing stream that's important for perception and object recognition, and a dorsal visual stream that's important for guiding the motor system. And what current multimodal models seem to have done is glue together the computations that occur in the ventral visual stream with language. What's currently missing are the computations that are occurring in the dorsal visual stream, computations that are really important for spatial reasoning and motor control. So I think an open question is, in their current form, in this sort of translation from pixels to words, can multimodal models ever really be able to spatially reason? I think there's potentially reasons to answer yes. Maybe they just need to be trained on different kinds of data like videos, and maybe spatial reasoning would fall out. But I think there's important reasons to answer no, and that's that language is a poor representational medium for spatial information. Vision evolved to guide the motor system, so maybe we need systems that interact with or simulate interacting with the world, like robots. And the final point I want to make is spatial reasoning itself is transmodal. We often link it to the visual system, but it can occur without vision, for example, in people who are blind. It has rich auditory and tactile inputs. So ultimately, to make progress in spatial reasoning in multimodal models, counterintuitively might have to separate the domain of vision from the concept of spatial reasoning. So I think that's my 5 minutes, and I look forward to talking more at our poster.
Our second presentation is by Dobrik Georgia, who will discuss the deep equilibrium algorithmic reasoner. Let's give him a warm welcome.
do we go next and three is left and right? Yes, I can put it. Give me one second. Okay, that should be done. Okay. Can you hold the microphone for me? Okay, sorry for slowing it down a little bit. So I want to tell you today about a bit more about algorithmic reasoning, for which I'm very thankful Peter gave a very nice introduction to. And if Peter did not mention it so far, in algorithmic reasoning, for good out-of-distribution generalization, you need to have a good, what we call algorithmic alignment. It's like the bread and butter, similar to how in GDL you have equivariances and invariances. Here we have algorithmic alignment. And particularly in our data, we want to align the property that after several iterations, you hit a termination of the algorithm. This is going to be an equilibrium. Further iterations of the algorithm, let's say you have a function that visits the unvisited nodes here, would make no change. This is an equilibrium, and we want to model this with the graph neural network by, in an implicit manner, by training it to find the equilibrium model. Now, a 10-second shout out to the Nina Institute in Montreal. We are not the only one working on this. And if you want to see a different viewpoint of this line of work, feel free to check out their blog post. Now, what we did in our data, it's fair to say, as we agreed with our collaborators, was reinvent the equilibrium wheel for the NAR part, because the equilibrium models and finding equilibrium points have been like long-standing research, and Zico Cotter, who just recently became head of CMU, he has a long list of data. Feel free to check out their research. But in essence, it's that simple. If f theta of x is your neural network and theta x is the parameterization, you just address this as a root finding, and you can use any root finding algorithm to find the zeros of g of theta of x, and thus find the equilibrium point. And against all the restrictions, I'm going to flash some data at you. We compared on 4 algorithms here, and we saw that the performance with respect to the baselines, including the more expressive baselines, is comparable. And what surprised us the most is that on tasks such as insertion sort, we were able to even outperform the baseline. And those results are on the CORS benchmark that are introduced. And last result I promised is that when you also use equilibrium finding, you don't need to align to every iteration of the underlying algorithm. And you can use fewer or sometimes even more iterations to find the solution. That in most of the time, this would also give you faster inference times. And in the case of insertion sort, we found that our model uses about logarithm number of steps, which is the theoretical lower bound that you can have for a sorting algorithm. Now, I think my 5 minutes are also running out of time. So if you want to hear more, or if you want to point me to the titles I have in my poster, or you wanted to argue with me about the needed, catch me at the poster session. Thank you.
Thank you so much, Delbert. And our final oral presentation is by Jai Ken, who will discuss the autonomous evaluation and requirements of digital agents. Let's welcome Jai.
Yeah, cool. Hello, everyone. This is Jia Yipan. I'm a first-year PhD student working with Elaine at UC Berkeley. So yeah, today happy to discuss about our recent work on enormous evaluation and refinement of digital agents. Yeah, thank you. Yeah, so how can I make it full screen? Oh, I think it's full screen.
Full screen, yeah.
Yeah. Okay. Okay, let's get started. So by digital agents here, we mean like models that are conditioned on natural language instructions to like browse the web or control the digital device to get things done for you. We care about such tasks for many reasons. For example, it's useful in our daily lives, but more importantly, like the vast open-ended digital world is also an exciting place to build the generalist agent itself. So we can just first look at how the community has been doing, right? So on the evaluation side, previous works have been built some fantastic handcrafted benchmarks. They are very useful, but because of its handcraftedness, so first, they are hard to scale, and secondly, there will always be a mismatch between the evaluation and the real-world deployment. While in our work, we actually show that vision language models are effective open-ended agent evaluators, which enables us to transform any in the wild digital environments into a benchmark or training environment. On the capability side, driven by recent progress in vision language models, recent SOTAs are usually built by prompting or supervised fine-tuning with human demonstration data. Well, in this work, we show actually autonomous evaluation enables autonomous agent improvement. We can significantly improve upon these base models through autonomous evaluation without any additional supervision. So we can I'll first describe how we like build these autonomous evaluators and discuss about agent improvement. So here is a typical trajectory we sample from WebArena. So given a user instruction like tell me the cause of my latest cancel order, the agent will execute on the browser step by step and finally derive at the final response. And just like how human judges will judge the success of the response. Basically, we just try to feed all the information into a model and ask for its judges. We experiment with two approaches. The first is an end-to-end evaluator. Basically, we just feed all the information into pretty advanced vision language models like GPT-4 Vision and ask for its judges. And it turns out to be pretty effective. Or if you prefer an open weight solution, we find like in the open weight domain, like if you first transform the visual information, like the screenshots, into captions first, and then do the reasoning in a text-only language model, it usually yields better performance. Yeah, and here are some numerical results of evaluators. So we tested on two domains, WebArena and Android. So on the WebArena domain, so our evaluator usually achieves around 80% agreement with WebArena's handcrafted evaluation functions. While on the Android domain, our evaluators achieves around 90% agreement with human judges. So these numbers, as we show in the paper, basically illustrate like the evaluation is effective. And next, I will talk about how these autonomous evaluators enables like agent refinement during both inference and training time without additional supervision. So to demonstrate inference time refinement, we choose a very straightforward algorithm called reflection. So here is a typical agent execution. And we first, after the agent finishes execution, we feed its trajectory, all the information into the evaluator. And in this case, the evaluator thing fails. And then we trigger the reflection algorithm, which is basically prompts the agent to say, hey, you made a failure, reflect on this failure and try again. So in this case, the agent tries again and derives at a new response. So we feed it again to the evaluator. And if the evaluator thinks like in this case, it succeeds, we will use this as the final response instead. So it's worth mentioning we do not rely on external evaluators, so there's no external supervision at all. So we tested it on the challenging WebArena benchmark. So the baseline is the previous SOTA, the GPT-4 based agent, which has around 60% success rate. And you can just look through the graph. So basically all evaluators improves upon that baseline, with the best GPT-4 vision based model improves by around 30%. We also tested with training time refinement. So we probably won't have time to go into the detail here, but the short summary is we tested a reinforcement learning algorithm called filter BC with our evaluator as a real function. So we fine-tune or we post-train the agent on both Android and iOS environment, and we find it basically yields around 70% relative improvement over base models with our autonomous evaluator. And that basically ends my presentation today. So we hope to convey you with two messages. First, vision language models are effective agent evaluators. And secondly, autonomous evaluation enables significant autonomous agent improvement. Yeah, I'll be around and happy to discuss more in the poster session. Thank you.
Just wait. Okay.
Good.
Make it large.
Okay, first a short announcement and then I'll introduce the speaker. So Professor Tom Griffiths was supposed to be the speaker today, and unfortunately he's a little unwell and is recovering. And in his place, we have Dr. Mark Ho, who is an incoming assistant professor in the Department of Psychology in New York University, and is currently faculty at Stevens Institute of Technology. He directs the computation and decision-making lab there. And he was actually a postdoc with Tom Griffiths at UC Berkeley and Princeton, where he received his PhD in cognitive science. So his research in Mark's research group combines approaches from cognitive science, social psychology, and computer science to study the general computational principles that underpin human problem solving and social cognition. So let's please welcome Professor Ho.
Mark, please go ahead. Oh, you can't hear?
Can't hear him yet.
All right, great. Can you hear me? Awesome. Great. Yeah, thanks so much for inviting me to talk. Yeah, Tom was feeling sick, so has asked me to present in his place, and I'll be presenting a bunch of work that we did together. So hopefully it will be related to the original version of the talk. Yeah, so today I'm going to be talking about abstraction in humans and machines, but I'm really going to be talking more about abstraction in humans first, and then we'll kind of circle back around and talk about abstraction in machines. The kind of overall context in which I want to think about abstraction in human cognition is just this observation that, when we look at human cognition, it's very general and very flexible. And that's particularly in contrast to, say, other animals, other species. For example, we know that other animals can do very sophisticated behaviors like use tools and can, do things like cooperate. And traditional AI systems, up until very recently, were also largely very specialized. So, for example, AlphaGo is very good at playing Go. Google Translate up until pretty recently was only able to really do translation, but you couldn't get Google Translate to play Go or get a Go playing algorithm to translate. But humans are kind of remarkable. And when we talk about the general purpose capacity of humans, what we kind of mean is that people can do all of these kinds of tasks. They can learn to do all these tasks. They can switch between them. And the set of tasks that I've listed here is ultimately a very small set of the possible tasks that a person could engage in. I think a big focus of this workshop is thinking about, okay, what are the basic elements of general purpose cognition, in particular, what is the role of multimodal representations, and how are the kind of the needs of multimodal representation shape. Oh, you can't see the slides. Okay. Let me know if you need me to do anything on my end. I can't hear you.
Can you hear me? Please go ahead.
Yes. Okay. Yeah, and so right. So, in trying to unpack and understand what makes general purpose cognition possible in humans, we really have to look at a lot of different processes at play, including multimodal representations. But I'm going to talk about abstraction and representation from a particular perspective today in my talk, and in particular, thinking about what is the interaction between abstractions and planning in human cognition and human problem solving. And planning is really important because it really underpins all of this capacity for flexibility, flexible problem solving, and flexibly reacting to contingencies in the environment. In particular, planning, is often characterized in the psychology literature in contrast to, say, habitual behaviors. So, for example, you can imagine that you drive to work every day, and typically you take a particular route to get to work, and maybe you can memorize that route. You don't really think about it much when you're driving, but the world is not static. The world changes constantly, and perhaps one day you're driving and the road that you usually take is closed, and so rather than just being stuck and not knowing what to do, you form a mental map of the town you're in, kind of bring details of the town that you weren't thinking about to mind, and start planning in that representation and thinking about, okay, well, since the road is closed, the road I usually take is closed, what roads are probably open? How can I navigate along those roads to get to the destination that I want to get to? And so clearly planning is very useful. It's a very important part of how we deal with everyday problems, and it allows us to adapt our behavior to changes in the environment and novel contingencies. But at the same time, planning is also a very computationally complex and difficult problem. And in particular, the difficulty of planning from a computational perspective is really summarized in the so-called recursive dimensionality, which in this case basically says that as you search further and further into the future, the space of possible sequences of actions that you could take grows very quickly. And so the usefulness of planning is always kind of balanced against its computational difficulty. And so a big question from the question of how do we understand human cognition, how do we understand human psychology, and also how do we reverse engineer systems that think and act like humans, is how do humans organize and access knowledge in a way that allows them to efficiently plan? How do we to the extent possible overcome the recursive dimensionality to get usefulness out of planning? And within psychology, there's obviously been a lot of work thinking about all the different ways in which people, different mental strategies people use to make planning efficient. So people will, not even rely on planning; they'll rely on habit, as I mentioned. Use model-free computations. Re-encode the state in a particular way. Use predictive state encodings, things like the successor representation. And so there are many different strategies that people use to make planning efficient, chunking actions, being selective about computations, using heuristics, sub-goals, and constructing simplified models of problems. And so this last one is what I'm going to focus on for most of my talk now. So this question of how do we think about representations in planning and abstractions in planning, I want to start by kind of outlining what you might think of as the classic model of planning, how people in AI and in cognitive science often think about the process of planning. And the typical model of planning involves, you're engaging with a task in the world, and you have a kind of default, you kind of have a representation of that task that's typically fixed. So for example, if you're trying to plan a move in a game of chess, you have a representation of the game of chess, of how the pieces move, the goal of trying to capture your opponent's king, and so on. And then given that representation of the task, you perform some kind of computation over that representation. You plan, you do tree search, and simulate possible sequences of actions that you could take and then choose the best one. The alternative model, or kind of augmentation of this kind of classic model of planning that we explored in some recent work, was to introduce this notion that people are not necessarily planning in a fixed representation of a problem. They're not necessarily planning in the kind of given representation of a problem, for example, in chess. Rather, they're forming what you might think of as an ad hoc or temporary abstraction or construal of a problem. They're construing the problem in a particular way, and then performing these kinds of planning computations over that representation. And so to kind of illustrate this, or to kind of give an intuition about how this works formally, we can think of this process of construing or forming a representation of a problem as a kind of meta reasoning or meta choice of how do I choose a good representation of a problem in order to plan within it. And that choice is really going to trade off two key things. So one is how useful is the plan that I get out of that representation, and the other is what is the cost of the representation. So I'll walk through this in kind of intuitively right now. And we can think of the value of a particular representation or construal or abstraction of a task as we're going to represent it as a kind of value function or utility function over different possible construals given a task. And so I want you to imagine that you're riding a bike, for example, and you're in a town and you're thinking about, okay, how do I get from some start location to some goal location? You would plan and then take a path. But if you think about it, you would never really use this kind of representation, the actual map or this kind of actual photographic representation of a problem to do planning in, because there's just too many details to actually reason about and represent. And so it's very costly. Even though if it were possible to use this kind of representation, the plan that you get out of it would be very good. And so from this perspective, if we think about the value of a representation as really having these two components, one is the utility of the plan that you get out of it, and the other is the cognitive cost. This kind of photographic, highly detailed representation, it could give you a very good plan if you were to plan within it, but it would come at this high cognitive cost. It'd be very costly to actually represent this amount of detail. And so you could have another kind of representation of a problem, a simpler representation. So for example, this is a representation of the same part of town, except you're only thinking about the roads. And if you're given this representation, you would plan within that representation and get out an optimal plan that looks something like this, and it would tell you to take the sequence of actions to get from your goal to your destination. But the problem is that even though this is a nice kind of a good simple representation that really removes a lot of the details, the plan itself is not as good as it could be. Rather, if the plan that you take here kind of takes you along a different road to get to your goal, rather than takes you along the most efficient path possible. And so this kind of is a good cognitive cost, but has a bad low behavioral utility. So what you really want is a representation that both is cognitively efficient, cognitively cheap, and also behaviorally useful, has high behavioral utility. So for example, if you're on a bike, you would want to think about the bike routes, because that kind of gives you the affordances in the environment that are most useful for getting through the environment to your goal, and thinking about to get through the environment to your goal. And so we can kind of think about, again, this trade-off in this space of different abstractions and refinements of a situation, where if you have a very highly refined, detailed representation of a problem, you might be able to get a good plan out of it at high cognitive cost. But also and then alternatively, you could have a simplified representation of a problem, but it might be the wrong simplification, which would give you a poor utility, but good cost. But what you really want is something that optimizes both of these terms. And so the kind of key idea behind this account is that people, when they are forming abstractions, they are balancing this behavioral utility and the cognitive cost in a way that is optimal or near optimal. And so to study this in humans, we developed a simple task that is similar to the navigation situation I talked about, where people are given a maze with a bunch of obstacles in it and need to navigate from some start location to a goal location. And what we're interested in is what is the underlying abstraction representation that people are forming of the problem. So for example, rather than representing all the objects in a grid, they are representing some subset of the objects in a grid, like this on the right. And so by casting this as a kind of optimal choice problem, or as a decision problem with a value function and so on, we can ask, well, okay, what is the optimal construal in a given scenario? And so we can calculate for these mazes what the optimal construal would be, and then compare those to human responses. And what we find is that people, there is a nice qualitative correspondence between what people respond paying attention to and what their what the model or what our account of kind of optimal construal or optimal abstraction says. And so so this is kind of a qualitative comparison. I'll just show you very quickly breaking it down by the objects that are predicted to be ignored by the account versus human responses. And what we can see is that things that are predicted to be ignored have people report not paying attention to, whereas things that the account predicts people would pay attention to, people report having high attention to, awareness of. So this notion of optimal construal is it's one way to kind of think about the relationship between representations and or representations and abstractions and computations like planning or reasoning computations like planning. We can also kind of revisit and think about other kind of puzzling phenomena in human cognition and human problem solving and how we seem to represent or abstract problems. So for example, there's an old set of results in psychology on what's called functional fixedness. And if you're not familiar with this idea of functional fixedness, the kind of original kind of canonical experiment for this was done by Dunker in 1945. And the basic idea is you bring in people into a lab and you tell them, okay, here's a table, there is a candle on the table, a book of matches, and a box of tacks. And your goal is to mount the candle on the wall and light it. And when you give this to people, they try a bunch of things. They do things like try to melt the candle to the wall, they try to tack the candle to the wall, but none of these work given the kind of causal properties of the candle and the box of tacks. The candle crumbles and so on. What you're really supposed to do in this situation is empty out the box of tacks, tack the box to the wall, put the candle in the box and light the candle. And what's kind of funny and puzzling about this is that when you tell people who've been trying to solve the problem for a while that this is the solution, they often kind of throw their hands up and say, wow, I should have thought of that before. That's so obvious. It's so obvious in retrospect. So they're not really learning something new about a situation. Rather, they seem to have thought about the wrong things in the situation. And one way to think about this is that they're using the wrong task representation of the problem. They're kind of thinking about things, they're forming abstract representations of things, but in ways that are not correct for the situation. In particular, they seem to be construing the box of tacks as a container of the tacks and not as a support for the objects or for the candle. And so to get at this idea using computational tools and kind of understand what's going on from a computational perspective, we developed a version of this grid navigation task based on the idea that we can form different kinds of abstractions of the same object in a very flexible way. So for example, if you imagine that you're at the airport and there are a bunch of terminals, you could think about each terminal at a very high level abstraction, just as this kind of big blob out there in the world that you maybe have to take a shuttle bus to and from. Or you can zoom in on any particular terminal and think about very more specific, more detailed and parts of it. For example, where the bathroom is, where the food court is, where your gate is, and so on. And so we designed a maze, one of these simple tasks that have this structure to it, where again, you're blocked off by certain objects, in particular these 3x3 blocks here and the black walls there. But the blocks also have a kind of more fine-grained, more detailed structure. They have notches in them that you can walk over if you want. And so this kind of having multiple levels of abstraction of the same scenario leads to potentially different behavior and different possibilities. So for example, in this maze on the left, you actually don't need to think about the notches to solve the problem. If you only think about each object as a block, as a 3x3 block, you're able to figure out, oh, I need to navigate over here to the right and go up. But now imagine that you moved this block up here. So the block is blocking this path. Well, if you only form a blocks only construal of this maze, then there's no way to solve it. There's no way to come up with a plan to figure out how to get to the goal. And so what you really have to do is form a blocks and notches construal of the maze. You don't necessarily have to pay attention to all the notches in this maze, but you have to pay attention to at least one of them to figure out how to get to the goal. And so we ran a pretty simple experiment just trying to understand the dynamics of this abstraction process in people. And what we find, and so what we did was we put people into one of two conditions. So in one condition, we had them do a bunch of these mazes that where you had to go through a notch to get to the goal, these notch necessary mazes. And so those necessitated forming an abstraction that involves both blocks and notches, versus giving people a series of what are called notch unnecessary mazes, where you didn't have to go through a notch to get to the goal, and you could only think about the maze in terms of blocks and notches. And just to be clear, both groups of people, given these sequences of mazes, these different sequences of mazes, they were introduced to the concept of the notches and the blocks. They knew about them. They even did some kind of very early trials where they had to use the notches. So they're coming into these situations with very similar, if not the same, kind of knowledge of how the world works. But we're interested in whether they end up using different abstractions. And so in this test maze, we gave them, or this series of test mazes, they had this structure where if you formed the blocks and notches, or if you blocks and notches construal of the situation and paid attention to the notches, you would realize that, oh, you can go through a notch to get to the goal more quickly than not. And if you formed the blocks only construal, you would only think to go the long route to get to the goal. And so there's an actual kind of behavioral cost to using the wrong abstraction of a problem. So we were interested in whether, as a function of this exposure to notch necessary versus notch unnecessary problems, people would be more or less likely to take these different routes. And what we find was that when they were given the notch unnecessary sequence, they were much less likely to go through the notch, indicating that people are really kind of locking into the simpler representation of the problem, only in terms of blocks, and that there's a kind of stickiness to it that prevents them from solving the problem in the most efficient way. And that this actually persists over time. And even by the end, some people are not taking the optimal route. So from a computational perspective, trying to understand what's going on here, there's this interesting kind of dynamic between action, planning, and representation or abstraction that's going on. And the way we approach this and try to explain what's going on is to say that people are kind of coming into the task with different kind of abstraction mindsets or abstraction strategies that they're using. And so, for example, if on some initial maze, they're only thinking about the blocks, then over time, they are continuing to think about the blocks. There's a kind of stickiness from problem to problem until they get to the end and kind of realize that, oh, there's a blocks. Maybe I can take a shortcut to get through this. And so the approach that we take here is to really think about, okay, what are these like latent construal or latent abstraction strategy dynamics that people are using in this kind of sequencing of problems. And we can think of this, again, as a dynamical system where there are kind of two mindsets or abstraction strategies that a person could be using. One is only blocks, the other is only notches. And the dynamics here are governed by different costs. So one cost is that switching is costly. It's easier to stay within a particular abstraction than to switch abstractions. The other is that complexity is costly. Blocks are simpler than blocks and notches, because to think about the notches, you have to think about the blocks. And so we were able to show that these costs, these kind of cognitive costs on the representation, on the abstraction strategy, end up explaining behavior. And you really need both costs to explain what's going on. And a kind of side result we found here was that reaction time is actually predicted very strongly by the complexity cost. So people seem to be really, so they take longer to plan when they have to think about more objects or more details of a problem, which is consistent with this idea that it's a costly, like representation is costly, and that the human brain has to kind of manage those costs in an effective way when problem solving. Okay, so just to wrap up how this, some of these ideas around general purpose cognition in humans and problem solving kind of relate to some of the themes of this workshop. As I started out, started talking out, when we think about human cognition, it's general, it's flexible, but it's also very efficient compared to a lot of AI systems. And there are many factors that could be shaping the processes of abstractions and type of abstractions that people form. And I think we need to really consider all of these when trying to understand how are abstractions in humans going to be relating to abstractions in machines. And so, for example, a very common way of thinking about abstraction, and that I think is really nicely summarized and demonstrated in this recent paper by Brendan Lake and Wei-King Wang, is that multimodal learning, just the data itself, trained on very general tabula rasa representations, can actually pick up on abstract representations. So training on both text and language, images and text, actually gets you quite far in explaining human data, but not all the way. I would like to propose or argue that really a very important factor in the types of abstractions that people are forming is this need to efficiently reason and plan and control and meta-reason about problems in a way that is adaptive but also reliable. And so that's kind of the theme of some of the work I talked about today. And another dimension to thinking about abstractions in humans that doesn't necessarily come out of the multimodal, thinking about things from a purely multimodal perspective, is that a lot of human abstractions are the result of cultural evolution and are kind of designed for cultural sharing and interpersonal interactions. So, for example, this work by Bill Thompson and some folks from Tom's lab, looking at how do different algorithms evolve in social cultural processes where people are kind of organized into different generations of learners who learn from one another over time. And a kind of key finding from this is that it's not necessarily the most efficient algorithm that wins out over time, but the one that also can be transmitted most effectively and most easily, and is kind of robust to errors in transmission. And so in thinking about the kind of abstractions that are relevant for machines, we should be thinking about, well, if we want them to be human-like, we should also be thinking about how do humans, what are the actual factors that shape human abstraction. And in machines, we typically focus on multimodality and kind of the nature of the data set, but also efficiency could be very important, the kind of efficiency of the representations as they're used in algorithmic processes. And then also thinking about the kind of cultural or social dimension to abstractions, which is their interpretability, whether or not they're aligned with human cognitive representations, and then also their explainability. So I want to end by thanking my collaborators on the work I presented today, Tom Griffiths, Jonathan Cohen, Michael Littman, David Abel, and Carlos Correa. And thank you all for listening, and happy to answer any questions if we have time.
Thank you, Mark, for that excellent talk, and special thanks to you for stepping in with such a short notice as well. We have time for maybe one question if anybody wants to come up and ask Mark. Wait.
Hi, can you hear me?
Yes.
Yeah, great talk. I was wondering, it seems like humans might change our construals of a task over time during the task. For example, the bicycle route, where you are in the route depends how you construe the task. Have you considered that in your research?
Yeah, so we're starting to look at that. If I'm understanding your question correctly, yeah, as we are doing a task, okay, so I guess there are two ways to interpret it. One is as we are doing the task, maybe we're even adapting our representation within task, right? Okay, so yeah, that's definitely something that we're looking at. And in some of the papers I presented, we actually do have some modeling that looks at the dynamics of construal over time and how you can think about, there's better or worse ways to kind of stage the representation over time and kind of integrate that with planning. But I think there's a lot more work to do there. In particular, thinking about abstractions and how the organization of abstractions can lend themselves to easier or harder kind of modification over time. So, for example, if you're navigating to if you're trying to get to the airport, you'll initially think about the airport in a very abstract way, but then as you approach the airport, you'll start thinking about it in more and more detail. And there is very likely a kind of more general principle at work there, which is that we need to organize our semantic representations of things in ways that allow us to kind of zoom in and out very flexibly to support, long-term planning, for example. But yeah, it's a great question. Yeah, there's more work to do there.
Excellent, thank you.
Okay, let's thank the speaker once again. Thank you, Mark.
Thank you.
Okay, a brief announcement. We have a very short 10-minute break now, followed by 2 more exciting keynotes by Lijuan Wang, who's going to talk about the recent advances in multimodal foundation models, and also Emilian Dupont, who will talk about how to do mathematical discoveries from program search using large language models. So yeah, see you in 10 minutes. Both those keynotes will be in person. So the keynotes will start at 10:35.
I'm Lian. How are you?
Good to see you. Good to see you. Very popular. Hi.
Nice to meet you. Glad you're here. Can I ask you how to pronounce your name?
I usually just go by Emmy. Like the first 2 letters, Emmy. You do like a French pronunciation, so it's Emilian. If you want to use yeah. You speak generative.
Around today.
Yes.
If you want to I will
we ended up having to basically develop like chunks of this. And this really only, so the size is only this only really became a problem for like 2 big
yeah, go ahead.
because you have a graphical size and then you have to change it.
Hi, Lijuan.
Oh, yeah.
Nice to meet you.
Hello.
Yeah.
Okay.
So I'll switch over. So maybe you just need to connect this.
HDMI or USB port?
It's
HDMI is here. Do you want a charging cable or?
I do have a charge. Mute and then.
Yep.
Now we're-
Maybe turn off the video.
Try something.
You want to turn on the video or?
But yeah, I haven't tried to make the model mainly because it's something.
The Zoom is showing.
I kind of use.
Oh, yeah. So-
Because this is the process. I mean, it's not really different because it's always from the concept like the graph of it shows you have to match the process. So it's not like I took that limited version of it. It's something you very excluding the graph.
Yeah. It's 10:30 and then we'll wait for a few more minutes. I think we're late.
Yes, yes, wherever you have access to a discrete structure computation on your head, either it's an algorithm or syntax tree processing or knowledge graphs, which are really popular nowadays. You can use similar kind of knowledge processing. So aside from what we're doing, Google research, the graph plane, really a lot of good stuff in there. These papers like talk about the graph, what your graph is talking to, everything that takes in graph structure and not structure and they so try to find the best way to that or something where they actually use an element this group of processor they found is doing the gradient so there's a lot of interesting things yeah, the architecture yes, the basic parts of the model are concerning the building blocks of but yeah, you can definitely do the same fine tuning just how much you did. We are now even showing like surely will push not like up the base or data, or they'll be able to do directly. Yeah, that's the one that yeah, it should be possible. Depending on what kind of connection you want, if you still have a chat down the line, I was going to get you this. Saturday or Sunday, I woke up at 3 hours morning and I started looking at my brain is. Put some email there, I'll get back to where some of the time.
There's so
yeah, it's also related to someone and they could that's great.
So yeah. So hello everyone. Welcome back after the break, and I hope you're having a good time at the workshop here today. So next up, it is my great pleasure to introduce Dr. Lijun Wang. She currently serves as a principal research manager, leading her own team within Microsoft Gen AI. After earning her PhD from Tsinghua University, Lijun began her tenure at Microsoft Research Asia in 2006, and later joined Microsoft Research in Redmond in 2016. Her research primarily focuses on multimodal understanding and generation, encompassing a wide range of areas from 3D talking heads to vision language pre-training, vision foundation models, and image video generation. As a pivotal contributor in vision language pre-training, image captioning, and object detection, her work has been integral to the development of various Microsoft products, including Cognitive Services and Office 365. She is a senior member of the IEEE and has published over 100 papers in top-tier conferences and journals. And she also holds more than 20 US patents that have either been granted or obtained. With that, let's welcome Dr. Lijun.
Hello, everyone. So it's a privilege to presenting here. I'm Lijun Wang. So I'm currently working on the multimodal generative model at Microsoft. So today I would like to share my understanding on how the vision foundation models get involved over the past few years. I want to talk about 3 models here. The first one is the CLIP model. The second one is the large multimodal model, LMM. The third one is the diffusion model. I think the fundamental question here we want to ask is how to extract intelligence from visual world. So when we look back, CLIP represents a paradigm shift when it was introduced in 2021. CLIP extracts the information at an intersection between image and text, at training both an image encoder and text encoder together. The past year has been marked as the rise of large multimodal model. So large multimodal model extends large language model with the sensory skills such as visual understanding, so that it can achieve stronger generic intelligence. Also, we want you to pay close attention to diffusion model, not only from the perspective of image and video generation, but also view it as a more vision-centered representation learner. I'm sure a lot of you are already familiar with CLIP. So CLIP was a big paradigm shift at the time it came out, because rather than needing handcraft labels to train a good classifier, which is time-consuming and painful to do, now we can leverage free-form text from the web to learn a model that is simultaneously a good classifier for all domains. So CLIP has proven to be an efficient learner to extract information from image text pairs. The past year was the year of a large multimodal model. Here, I want to make connection between the large multimodal today with the early vision language models. Early vision language models serve as the prelude of the large multimodal model. These slides basically show you the evolution of early vision language models, from Uniter proposed in 2019 to Flamingo, COCA, and the GIT, which are proposed concurrently in May 2022. First, I want to take a GIT as a case study for the image-to-text generative model, which takes image as an input and output is a text sequence. Most of today's LMM model variants share a very similar model architecture and training objective. In terms of the model architecture, the model typically consists of an image encoder to extract the visual features and a language model to decode the text sequence. The vision and the language modalities can be potentially connected by trainable connection modules. The image encoder and the language model can be either trained from scratch or initialized from pre-trained models. Training objective typically employs an autoregressive loss on output text tokens. For attention map in the transformers, image token can attend to each other, and the current text tokens attend to all image tokens and all the previous text tokens. Flamingo is another example to train LMM with interleaved image text sequence. So it connects the frozen pre-trained image encoder and the language encoder by adding novel architecture components in between. Flamingo is trained on a mixture of complementary large-scale multimodal data coming only from the web, without any data annotated for machine learning purpose. After the training is done, Flamingo can be directly adapted to vision tasks via simple feature learning, without any additional task-specific fine-tune. Now we come to the year of 2023. OpenAI released GPT-4, and the era of large multimodal starts from the GPT-4V model. In the paper, The Dawn of LMMs, we analyzed the GPT-4V model to deepen our understanding of the LMMs. OpenAI acknowledged that the dawn of LMM's preliminary exploration with GPT-4V by our colleagues at Microsoft covers a plethora of practical observations and strategies for using GPT-4V. OpenAI has included this paper in the GPT-4V body of work. In our exploration of GPT-4V, our focus has been using qualitative results to offer a snapshot of GPT-4V's new capabilities and potential emerging new use cases. Our objective here is to uncover and preview what GPT-4V might already be capable of, even though these novel capabilities may not yet be fully reliable. From our study, we see that GPT-4V has significantly advanced the state of art in areas that have baffling computer vision community, including zero-shot, open vocabulary, task unification, free-form image text interleaved input, and in-context learning. Here, I would like to highlight a few scenarios and new user cases that can be potentially enabled by the emerging capabilities of this model. The first one is the visual pointing. We know that pointing is one of the earliest hand gesture a baby learns for communication. We found that GPT-4V can well understand the visual pointers that directly drawn on the image. Based on this observation, we proposed a novel model interaction method. We called it visual pointing. The core idea is to directly add image pixel space to draw visual pointers or syntax as human referring instructions. So as the example shown here, GPT-4V can comprehend the question and accurately respond that the blue arrow is pointing to the running shoe. So it intuitively links objects indicated by the arrow to its respective objects. Also, other emerging capabilities like coding with vision. So GPT-4V can generate a Python code to reproduce a line chart. We also find the GUI navigation is quite interesting. GPT-4V can interact with and navigate through the graphical user interface of a computer or smartphone. In the paper, we also explore the potential of GPT-4V to complete complex tasks, such as web browsing, online shopping, message responding to notifications. It can also handle like incoming call and message notifications to a computer screen effectively. Also, it shows potential for embodied AI to actively engage with dynamic physical environment. To paint a clearer picture, so imagine GPT-4V is powering a home robot. In this setting, the AI can interpret appliance operating instructions and also perform task-oriented navigation through the house. In the months following the proposal of this model, we observe a surge of instruction-tuned open source LLMs emerging as a new line of research. Here, I want to use Lava as an example, open source LLM example. A similar idea is also proposed in its concurrent work, Mini-GPT-4. The network architecture of Lava is very similar to the network introduced in GIT. Lava connects the pre-trained CLIP model, CLIP visual encoder, and a large language model Vacuna, and also add a simple projection matrix, which is a linear projection layer. It has two-stage instruction tuning procedure here. In stage 1, the pre-training for the feature alignment. So only the projection matrix is updated. In the second stage, fine-tuning end-to-end, both the projection matrix and the language model are updated. Today, the landscape of LMMs can be well tracked on the LMM leaderboard. As of last week, there are 30 open source LMMs and 21 proprietary LMMs listed on the MMMU leaderboard. On the MMVAT leaderboard, we also observe rapid progress, daily and monthly, with the latest GPT-4o reaching a total score of 69.7. Open source models are also catching up quickly, can achieve a score of 62.8. Here, I want to talk a little bit about the I/O modality of this new model, GPT-4o. So while large multimodal extends the large language model by adding visual modality, it's natural to further extend it to go beyond just vision and language. So GPT-4o is a step forward, moving toward a much more natural human-computer interaction. It can adapt inputs in any combination of text, audio, image, video, and it can also output combination of text, audio, and image. So it would be interesting to investigate what additional capabilities for a model combining all these modalities together. What can go beyond the current capability. It also we want to understand how to make the native integration more efficient, and also let different modalities can enhance each other. LMM have also inspired many new research areas, such as visual prompting, with its representative work on SOM, and also multimodal agent. Multimodal agents for video understanding, for generating, automatic generating audio descriptions, for GUI navigation, as we can see in the paper, MMVID, MM Narrator, MM Navigator, as well as for visual design and creation with feedback. Next, we will talk about the diffusion model. If we see LMMs are adding image condition to language generation, diffusion model are the opposite. It's more like adding text condition to image generation. So we see that diffusion models are important to vision foundation models, not only from the perspective it's for image generation and audio and video generation, but also it can serve as a more vision-centered representation learner. A paper came out a while ago called "Your Diffusion Model is Secretly a Zero-Shot Classifier." The basic idea here is even you are modeling the distribution of image given text, the model can be converted into a classification model. This approach is somewhat similar to CLIP. Given an image and a candidate caption, you can use the diffusion model to compute a score for how well the image matches the caption. While this method is more computationally expensive than CLIP, it provides a compatibility and a similarity score between the image and the candidate caption. The paper also demonstrates that stable diffusion can achieve good ImageNet prop, which is a surprising result. In September 2023, DALL-E 3 was released by OpenAI. Modern text-to-image systems often ignore certain words or descriptions, forcing users to learn prompt engineering. DALL-E 3 represents a significant leap forward in generating images that precisely adhere to the provided text. I'm very proud to be part of the DALL-E 3 team working closely with OpenAI to develop this model. The key takeaway here from DALL-E 3 is that training on ultra-descriptive captions makes the diffusion model more compute efficient, even when measuring the quality of samples produced with shorter captions. Here, I would like to quote Aditya's words here. The observation also suggests that we can get a better unconditioned model by using ultra-descriptive captions as scaffolding, even if we don't use ultra-descriptive captions at inference time. In the past year, we also observed diffusion model has made significant advancement in video generation, progressing from low resolution to high resolution, from generating 4-second clips to 1 minute long video with character identity preservation, much better coherence, and also 3D consistency. The most important message, I think, from the Sora team is that their results suggest scaling video generation model is a promising path towards building general purpose simulators of the physical world. I personally am a strong believer in this direction. So to summarize here, today we discussed about 3 models, which I think are representative of the recent advances in vision foundation models. CLIP learns an image encoder and text encoder together. Large multimodals connects an image encoder with a text decoder. It also called a language generator, while diffusion model consists of a text encoder plus an image diffuser. So there are open questions, open discussions for the word model. So we are not sure which model will ultimately lead us to the perfect word model, but we're pretty sure it will require a lot of innovation from everyone here. So yeah, that's all of my talk. Thank you.
We have time for a few questions, and please come up to the podium to ask if that's possible. Do you want to come up and ask? Yeah.
You can ask there and maybe.
Okay, yeah, sure. Sure.
First, thank you for that. So looking at GPT 4.0 and Gemini 1.5, the capabilities in as LLMs are LMMs is really outstanding. Where do you see the gap today? Like, what do you think is their main gap to like general understanding of vision and multimodality? I mean, where do you see the pitfalls today?
We can repeat the question.
So I think let me try to repeat the question. So you say that the recent model from OpenAI and also from Google actually show very impressive results. So the question is that what is the pitfall from the current model to the ultimate general purpose multimodal model? Yeah, that's a very good question. I think it's a very open. I think this is a very open question as well. I don't see that we have good answer to say that the large multimodal will be the right direction, lead us towards the world model. Because I think eventually we need to solve the world model problem. So still, my view is a large multimodal is still a very language-centered model. So it do have limitation. Like in this workshop, we discussed all the abstraction images. And also like when we analyze, for example, GPT-4V, when we prompt the model, try to read the clock, the analog clock, it's very difficult. So I don't see that the model can solve many real world problems are unsolved. So that's why I think it's very open. So I don't think that today's large multimodal will finally lead us to the world model. So we need innovation here. Yeah.
Yeah, so I do agree with the progress we have seen in these foundational models, but I do have a question. It's like, given that these models are being trained on billions and billions of images, or first, how do we make sure that we're not putting ourselves, in terms of all these benchmarks that we see, how do we make sure that we're not actually testing on the training set in such a way, right? How do we make sure we haven't seen images on the training time that are very similar to the things we're testing? Any thoughts on that?
I'm trying to rephrase your question. So the question is that the model right now is training on a very large scale data set. So billions of images and text from the internet. How can we make sure that when we do the evaluation, we don't have any leakage from the training data, right? So to those benchmarks. So for those benchmarks, how can we make sure that we truly evaluate the quality of the model? So I think that's very good question. So I think the how to evaluating those new models, actually right now I see it becomes a very active research area. So we do need people to propose and develop a new benchmark, new evaluation, because they also have new capabilities which that the current benchmark cannot evaluate. For example, when we work on the paper, the down of LMM, we try to make sure that all our examples, all our samples are absolutely not included in the training data. We use a lot of our photos, our own capture photos, or the images after April 2023 to make sure that there is no chance that those images have been seen in the training data. But still, I believe that now we have the 4.0, right? 4.0 have more modalities integrate together. It definitely need a new benchmark, new evaluation metrics. And I think, people are working on it right now. So I don't worry about that. So.
Any other questions?
right now on not the large model, they like training a very large scale data, and it's they don't have any idea about physics law when let's say Sora when they generate the video, they don't have any idea about the physics law of the video. Is there a moving what should be the physics law for that? And do you think like the big model can address that problem and in the near future, then we combine like physics driven approach and data approach together to do the better?
Let me try to rephrase. Okay, so I think the question is that do we see that Sora like model can learn the physical law or any true physics be learned in the model? Yeah, so that's a very good question. So I think the OpenAI sent a message, they believe in that direction, but does that not mean that today their model can do that? So when people look at the current Sora results, when it's tried to do 3D reconstruction from the video, actually the quality is very poor. That means right now the 3D consistency in that model is still very poor. But it's just point us to a path that maybe when we scaling up this video generation model, that's a way for us to learn the word simulator, to learn the physical word, because we need a way. Because if we ask the question whether the larger language model is the way to learn the simulator versus Sora, this type of video generation to learn the word simulator, which way do you think is the more promising way, right? I think that's a open, very open question. So yeah.
The future of your video about how could the video generating model capture the multi-level logic consistency, like their short level, like short-term logic consistency, like it will like one person is working below like left leg first and then right leg, but there are long-term logic consistency, like this person needs to do something physical. So how does the video models capture both logic consistency?
Yeah, so let me try to rephrase the question. So how do we see that Sora like a video generation model can ultimately learn the multi-layer logic consistency, right? Yeah, so I think that again, I think I feel that the word model really have many share many common feelings. So people want to see that how we can have a model can truly learn this kind of physical consistency, logic consistency, everything, right? I think that's the word model. So I think it's a video generation. I think currently is a promising path. Like imagine if we can given an image, if we can predict, anticipate what will happen next with this static image, that basically answers your question. So like at one level, you say that people will, which leg the people will move in next, right? And also it will answer that maybe the ball will bounce the floor and then what, right? But there are many things will happening when you try to force the model to predict the next frame or video. So yeah, I see that it's a promising direction to learn the word model.
My question, so it seems to me that short-term logic consistency is a little bit different from long-term consistency, because to capture the long-term, you need some like abstract understanding of the signal. Like you have like language and understanding. So how does the vision model actually capture?
Oh, that's a very challenging question. So I think that the try to rephrase the question is that the video generation currently, we can try to model the relatively short term, right? Predicted what is happening next. But what about the long-term planning, long-term logic? Yeah, that's a challenging question. I don't have a good answer, honestly. So I see that all the future directions do need all the researchers in this room and also in CVPR to think about and to solve it together.
All right. So in the interest of time, we'll thank Dr. Wong right now and then move on to the next speaker. Thank you.
Yes, thank you. Thank you.
including online bin packing, which is kind of a root node problem for lots of downstream tasks, like scheduling jobs and clusters and everything. Okay. The voice is okay, or?
We're still figuring out the online
Okay,
part.
sorry.
Now it's okay.
Okay, cool, yeah. Yeah, so kind of at a super high level, what FunSearch does is it combines a large language model with an evaluator. And so a lot of problems kind of allow for fast evaluation. You can kind of check if a solution is a solution quite fast, but actually finding this solution can be pretty difficult. And so what FunSearch does is we combine an LM that tries to generate loads of solutions with an evaluator that tries to guard against incorrect solutions. So LMs, famously hallucinate and say all kinds of crazy stuff, but if we have a formal evaluator that can check if something is correct or not, or how good it is, then those two can kind of work in tandem to improve things. And so what we have is some kind of iterative improvement loop where like an LM tries something, an evaluator tells it whether it's good or not, and then they kind of continue working together in that way. And so at a super high level, let me get a pointer here. You kind of give as input an evaluate function that evaluates a solution for a certain problem you care about. And then you have this FunSearch loop that does loads of things. And then eventually a solve or a solution comes out, and that solution is hopefully good and useful for your problem. So this is obviously all like very high level. But I think the easiest way to illustrate it is through an example, because it's actually very simple when you just have something concrete in mind. So the example that I was thinking of focusing on is this capset problem, which is one of the mathematical problems we try to tackle. And it's quite simple to explain. So the problem is just to find the largest set of points on a 3 to the d grid, such that no 3 points are in line. So for example, in 1D, a 3D grid is the 3 grid is just 3 points in a line. In 2D, it's a 3 by 3 grid. In 3D, it's a 3 by 3 by 3 grid, and so on. And within this grid, you try to place as many points as you can, and you want to make sure that no 3 of them are in a line. And that can sound like a very toy-ish problem, but it's actually surprisingly very deep. And yeah, many mathematicians have worked on it, including Terence Tao, who's obviously a very famous mathematician. And he once said this in a blog post that's perhaps his favorite open question. So it's mathematically interesting problem. And so we're trying to see can we use FunSearch to tackle this problem and improve the best known constructions within this. And yeah, just some technical detail. This 2D grid is like we're doing addition modulo 3, but it's not super important. But just to be clear about what we're trying to do. So, okay, we can start with an example again. So this capset problem in dimension d equals 1 is just three points here in a line. And we're trying to place as many points as we can without creating 3 in a line. So first thing I do is add 1 point. All good, no 3 in a line. Add a second one, still no 3 in a line. But obviously, if I add a third one here, then these 3 are going to be in a line. So it's no longer a valid capset. So then from this, we know that the largest possible capset for dimension d equals 1 has size 2. And then we can repeat the same thing in dimension d equals 2, for example, here. So now I have a 3 by 3 grid. I'll try to add some more points. I'll add the point here, all good. This one, all good as well. I can add one more. But at this stage, if I try to add any other point, 3 are going to be in a line. So for example, if I add 1 here, the diagonal is going to have 3 points. So we're no longer allowed to do that. So it turns out in 2D as well that the largest possible capset has size 4. And at this stage, this is when I first saw this problem, I thought, okay, well, this is super trivial. All you need to do in any dimension is just to take any axis, add 2 points, and then you have a set of 2 to the d points, and that's the largest capset you can find. But it turns out already in dimension d equals 3, you can do better than this trivial solution. And crazily, there's actually more space for you to put in points without creating 3 in a line. And so the largest capset in d equals 3 has size 9. And this is illustrated here on the side. So all these gray highlighted points are the capset, and you can count that there's 9, and you can also verify that none of them are in line. And maybe some of you recognize the card game set here, which is very closely related to this problem as well. But yeah, so basically this quickly becomes non-trivial, and there's lots of interesting structure that comes out. And what mathematicians in general care about is what is the largest capset in size arbitrary d, not just in a given one. And it turns out that even for dimensions 7, I guess, yeah, 7 and above, the size of the largest cap set is just not known. And it's kind of an active research area trying to find better solutions to this, and also ultimately, like asymptotically, as d goes to infinity, what's the largest cap set you can have. And so what we were going to try to do is to just discover better constructions with this. And so just 2 properties that are very interesting about this problem, which we'll use in our setup, is that we can easily verify correctness of a solution. So if I give you a set of points, I can very easily tell you if it's a cap set or not. I just check if there's 3 points in the line or not. If there are 3 points in the line, it's not a cap set. If not, then it is a cap set. And I also have a signal of how good my solution is. So if you give me a set of points, I can just count how many points there are. And since we're interested in getting the largest possible set, this is kind of a score or a measure of how good or how well I'm doing. So these 2 things together just means that we can write a very efficient like evaluate function. So given a proposed solution, I can evaluate it very efficiently and tell you if it's good or not. Okay, but now we know how to evaluate something, but how can you actually find a better solution? How can you improve solutions here? And this is where the large language model comes in. So the kind of key idea that we had in this paper was to use an LM to kind of guide a search in code space, in the sense that we describe solutions in code and ask the LM to improve these solutions. And then we use the evaluate function to test whether these solutions are correct and how good they are. Here's a super simple example of how this works. And this is, I'm not even simplifying this. This is actually how it works in practice. So it's very simple. But so here, for example, I just wrote a Python function that builds a cap set. So say in dimension d equals 2, for example, we had before the grid. What I'll do is I'll just iterate over all elements in this grid. So for example, the 3x3 grid. And then I'll add an element to the cap set if this function is in set, is true. So it takes an element and tells you whether the function is in the set or not. So all the kind of like reasoning and intelligence happens inside this function here. And then I'll have an evaluate function, which just takes a set of points and then builds it using this function we had up here, and then tells me, is it a cap set? I'll check if there's any 3 in line. And then how many points are there? Just the length of the list. And then this isn't set function here is where all the cool stuff happens. And in this case, I just wrote this. There's no LM. I just decided a good heuristic might be in the first dimension, we want to make sure that's 0, and then the other dimensions maybe less than 1. But it doesn't really matter what you start with. The LM will kind of improve on it. But I just put this in here as a simple example. Okay, so now we have some code that you know tries to build a cap set. But how can we actually use an LM to improve it? And so we did something that's extremely simple, and to this day I'm still surprised it works. But you basically first take fun search, run this for the cap set, and then you take fun search here and run the evaluation, and then we modify this prompt just to add a v0 to this function we had here, and then we copy the function definition and add a v1, and then we just add a doc string that says this is an improved version of the v0, but we leave the function body empty. And maybe, at this point, you can kind of see where this might be going. This looks a lot like a prompt to an LLM, where you have kind of a context and there's something missing, and you want the LLM to fill out whatever's missing. And so that's exactly what we do. We just use an LLM to complete this function given the overall prompt. The LLM is told to improve stuff, so that's what it's going to try to do. And so, for example, the LLM might generate something like this, which is a slight modification of what we had before. And then we can check how good is this? Like, does it work better than what we had before? And because we have an evaluate function, we can really easily do this, right? So we just run the evaluate function in both of these, and it turns out the first one gives you a cap set of size 2, and the second one gives you a cap set of size 4. So the second one is actually better than the first one. And so we now have an improvement, but we want to continue improving, right? There's no need to stop here. So what we do is we simply take the v1 function and replace it, the old v0 with that one. So we swap it up here. And then now we just have the same prompt again, where we want to improve the improved version. And we again prompt the LM to improve the improved version, and then hopefully get an even better solution. And then you just continue this forever, or until you're happy with your solution, basically. So you just keep iteratively improving every time, and you make sure that there's actually an improvement by having this formal evaluator. So yeah, so that's basically the whole thing. That's how it works. So it's very simple. There's a few details that I kind of didn't mention here. One is that in practice, we don't have just like one prompt that we just iteratively improve. We have kind of a population of prompts, and then we use evolutionary search to kind of like evolve the space as opposed to just following one path. So for example, if we had this V0 before, we might sample, say, 5 V1s here from the LLM. We'll score each of them using the evaluator. And then we then kind of keep each of these 5. And then for the next iteration, we'll sample randomly some of these ones we had, usually proportionally to the score. So we want to sample something that's better more often, since that might help further. And then we just chain together these mutations, and then eventually the hope is that we'll get close to somewhere good. So here we sample something, we sample the next one, and so on. And the hope is that eventually we'll get close to some optimal or best known solution, or ideally even better than the best known solution. And so, yeah, this all sounds very simple, and the question is whether it works. And it does work, at least for this capset problem. So what we managed to do is, first of all, match the state of the art up until 6. And for this, these are known to be optimal, so it's not possible to actually improve. But for dimension 7s and above, we can improve. And in dimension 8, we're able to find a better construction than the best one known by mathematicians. And so, yeah, I guess there was also a question earlier in this workshop about, you know, you can just be regurgitating the training data, but we know that this is just simply not a known construction. So it's for sure not in the training data. So this has definitely pushed something beyond what is previously known, which, yeah, we thought was pretty cool. And another cool thing is that we're also able to improve like the asymptotic bound as n goes to infinity. And the way we did that is through some other kind of finite construction that's a bit different from a capset, but similar in flavor. And if you recursively apply this construction, you get an asymptotic bound. But the cool thing is that mathematicians usually care a lot about this one, and we're able to improve this also using this fun search method. And I mean, this would be like a publishable mathematical result if this were found by a human, which is pretty cool, that we can do this with an LLM, and that it has the kind of reasoning abilities to do that. And another cool thing about this is that we can also kind of have a human in the loop for a lot of this stuff. So in general, if you have computational search methods, what you would get is just a solution. So here I printed this like capset with 512 elements. So it's just a list of 8-dimensional vectors, and there's 512 of them. And so, I mean, if you look at this, it's not really clear. Like, I mean, there might be some symmetries, there might be some structure, but it doesn't pop out at all. And it's just not clear what's going on. And the cool thing with fun search is that we don't just generate a solution, we generate a function that generates a solution. And so here, with fun search, we can actually look at what the LLM has written and try to understand what's going on. And the really cool thing is that it turns out that there's lots of very interesting structure, and it gives you an understanding of what this set actually is like. This, you know, lots of symmetries, there's lots of cool things like that that we found. There's also some links to how some lower dimensional sets were constructed by other mathematicians. And this kind of part of it is quite exciting. And to mathematicians we worked with, this was actually the most exciting part, that you can actually look at what's going on, because the LLM just writes code that you can read. And so, yeah, to put this in some context, to some extent, you can call this like the first scientific discovery with an LLM, in the sense that it's provably new. Like, it's definitely not in the training set. It's an unknown construction. It's verifiably true. We have a formal procedure for checking this is actually a new construction. And it's a relevant scientific problem in the sense that lots of mathematicians have worked on it, and it's quite like it's an active research area. And the second part is that this allows you to kind of discover understanding about the problem, not just like a fact. Like we could just say, oh, we discovered a 512 size capset in dimension 8, but this actually says, oh, it has all these interesting symmetries, there's all this cool stuff going on, and that's what mathematicians ultimately care about. They care more about understanding than facts. And we actually worked together with a mathematician, Jordan Ellenberg, who's also written lots of cool books. But yeah, one of the things that he mentioned was that he really liked, we sent him lots of fun search functions, and he would look at them and be like, oh yeah, but there's this symmetry, and then there's this like thing that's related to some other construction. And yeah, as he says here, when he studies these things, he actually learns something. And one cool thing is that this asymptotic bound we found was actually from us generating a functional LLM, looking at this function, noticing that there was this like kind of symmetry in the dimensions and a permutation, and then thinking, oh, maybe this is the kind of solution we should look for with the symmetry. Then we enforce the symmetry, so the LLM starts looking only for solutions with the symmetry, and that's how we ultimately found the better solution. So this is, yeah, literally LLMs and humans working together, like giving each other ideas, and then eventually getting a cool new result. So yeah, so and it's not only for math that we're able to use this approach. So we also tried it for more kind of practical problems, I guess you could say. So one of the first ones we tried is this online bin packing problem, which just asks if you get loads of items coming in and you have a fixed number of bins, how do you place each item into a bin such that you waste as little space as possible? So here the red one will come in, you try to pack it somewhere, then the blue item comes in, you pack it somewhere else, and so on. And yeah, this problem has loads of applications. So whenever you try to schedule a job on a cluster anywhere, you load containers onto a ship, you design chips, and so on. Like this thing happens in the background. And so we're trying to figure out ways to improve this and see if this was possible. And so the way this is usually solved is using these things, these kind of heuristics, where you basically, given an incoming item, you choose which bin to assign the item to based on heuristics. And one very classic one is the best fit heuristic, which just says, whenever a new item comes in, just put it in wherever it will fit the tightest. Like after you put it in, what's the tightest fit? And so here, it would be putting it in the red thing on top of the blue one, because after you put it in, it's like a relatively tight fit in this box. And the cool thing is that these heuristics are, you can just basically write as simple Python functions as well. So in this case, we can just express the heuristic as giving a score to each bit. So if I have an item coming in and a bin, I first check, can the item fit in the bin? If not, then this is a terrible bin, so I'll just put infinite score. And otherwise, I'll just return the remaining space after I add an item to the bin. And you want to have the tightest fit, so you want to pick the one that has the minimum score here. And again, this is just a simple Python function that we can use to start like a self-improvement loop with an LLM. And so here we can just improve this function again with fun search, but we evaluate it on like data sets of bin packing instances instead of a single thing like we did for the cap set. So here we also need some generalization, right? We need to not just make it work for one single set of items, but for general distributions of items. So we also do some more like train test evaluation, which is, I guess, more of a classic machine learning approach. But otherwise, the procedure is basically exactly the same. And yeah, so a cool thing is that we're able to find the heuristics that consistently improve on these classic heuristics, particularly for large data sets. And here's an example where at the end we pack with 5 bins instead of 6 with the best fit heuristic. And one kind of cool thing that, again, we can look at the heuristic, right, and see what fun search is doing. And one thing it does that's pretty cool is that best fit just always tries to find the tightest fit, but fun search tries to find a tight fit, but only if it's really, really tight. Otherwise, it doesn't. So for example, here it puts best fit puts a green item here because it gives a tight fit, but the tight fit is actually not good because it leaves a very small gap that's unlikely to ever be filled with another item. So what fun search does when the green items comes in, puts it over here and then says, okay, now if I have a really tight fit with the item, then I can put it there. But this space is actually wasted now because we might not ever see a small item that'll fit here. And this kind of reasoning is quite applicable across lots of things. So again, the interpretability factor is quite useful. Yeah, this is also true, just, across data sets. So we have a few benchmarks here. This percentage is basically like, you can think of it as the excess bins over like an Oracle optimal solution. And you can see that we have much less excess than these classical heuristics. And particularly for instances with like 100,000 items, we're near optimal. And so this also means that for downstream applications, we can save resources and yeah, hopefully make things better. Yeah. And so one other thing I just want to touch on, which I think is quite important, is also some of the limitations of this approach. So one thing is that experiments are quite expensive. So for example, to get this cap set, we need to sample the LM 1,000,000 times. And yeah, I guess LLMs are big models, and yeah, they can be expensive to sample from. So sampling 1,000,000 times from LLM to get, I mean, arguably to get a new mathematical discovery could be maybe worth it, but yeah, it's not always clear exactly what the trade-off is. And I think it's pretty clear that there's a lot of wasted sampling. Like we kind of, yeah, if you look at the samples the LM generates, some of them are just like garbage, and some of them are very similar to what was there before. And there might be better ways to actually sample from the LM in a kind of a smarter way. Another thing is that we're kind of currently quite constrained to generating quite short Python functions. So we had this like V1, V0 setup, and usually we generate, Python functions that are like 10 to 15, maybe 20 lines. But this is not, yeah, maybe we want to generate an entire code base, we want to generate new libraries of functions. And I guess, yeah, this work doesn't have too much to do with vision right now, but I guess in the spirit of this workshop as well, in multimodality, we also might want to have things like you want to generate, say, visual signals, or you want to evaluate visual signals. And so currently we're quite restricted in the sense that we just have these short Python functions, but what we ultimately want to do is make it much more general, like natural language, yeah, multimodal inputs, and so on. But we're just constrained to being able to like needing a kind of an evaluation function. So that's also another kind of open question if you use other modalities. And the third point is also that we need like a fairly fast evaluation function. So for example, a few things we've tried, maybe evaluation is on the order of minutes, but every time you generate an LM sample, you need to evaluate it. So if evaluation takes a day on 1,000 GPUs, then yeah, you're not going to be able to run this because it'll just be too expensive. And so I think like points 1 and 3 are quite related in the sense that we want to make it more efficient, especially if we want to move to like more vision-based tasks that are probably more expensive. And one last thing that was quite interesting to me is that using better LLMs actually doesn't improve performance. So I feel like this is a very standard thing across all LLM literature. Is like you use bigger, better LLMs, then usually downstream tasks always get better. But we did not see this happening for us. And this kind of, if you use a really bad tiny LLM, it doesn't work. And there's a point where there's kind of a phase shift where if the LLM is good enough, then it starts working. But after that, moving to like the biggest, best frontier models doesn't actually improve performance more. And that also suggests that maybe fund search is not really taking advantage of like the intelligence or reasoning capabilities inside these LLMs. And so this is also something we want to work on. And maybe if the LLMs can be a bit smarter, we also wouldn't need 1,000,000 samples to begin with. And another kind of aspect that's interesting here is that we also have like an inference cost intelligence trade-off, I guess, here. So we could use a worse model than sample it 2,000,000 times for the same cost that a better model sampled 1,000,000 times, for example. And it's not always clear what the right trade-off is. So yeah, compared to some other LLM tasks, this is a bit of, yeah, there's some different trade-offs and things to think about here, which is slightly different. And also another thing, I don't know if I have time or if I can do that, but one thing that's quite cool to look at is actually looking at like an example trace of what the LLM does. Maybe this works. Does that work for? Yeah, so I guess the LLM tries loads of different things. So here, this is one of these capset like problems. And just to see what it does. So the LLM starts, this is what we just feed the LLM. This is the function it starts with. It's just really stupid. It gives 0 on every input, doesn't do anything interesting. But then we can look at what kind of mutations the LLM does. So it might do something like this, which improves the score. And then you can go further down the tree. Then maybe it does something like this here. And one thing that's interesting is you can kind of see at some point it kind of starts to converge on something interesting. So this looks like it has some interesting structure. And then, it slightly improves it here by adding some other crazy condition for this particular problem. And then for the last one, it gets something like this. And this one at the end is the construction that gave us this asymptotic bound, ultimately, like this best result. And so, yeah, maybe this is not the most interpretable function ever, but you can look at it and gain some understanding of what's going on. But it's also interesting to see how the LM got there in the first place, and also to see things that tried, like over here, that just didn't really work. Yeah, so it's quite fun to actually look at this evolutionary tree and try to see what's going on when the LM creates its samples. Yeah, so this is kind of what we've been working on so far, mostly in like more mathematical and computer sciencey type stuff. But the idea would be to also expand it more broadly to other domains. Yeah, that was it. Happy to answer any questions. Thank you.
Picture that you put up, the blue and red sort of smooth picture. It looked like there was sort of an optimization surface.
Yeah.
But and maybe I missed it, but it didn't look like there's any place here where you could calculate a gradient.
No, yeah. So I also, yeah, this is a very like yeah, it's a bit maybe slightly misleading. It's like a very toy kind of diagram here. So I guess this would be like the space of Python functions, and would be kind of like starting at a certain Python function, doing random mutations around it, and then we can score them. And the hope is that, you know, highest scoring Python function will be a good stepping stone for an even higher score Python function. So in that sense, there's a gradient in the sense that you can like iteratively improve things, but it's not necessarily true that like a solution that gets you 90% there will actually be good to get you to 100%. And so what we do in practice is that we keep like quite a wide range of points. So we keep something like even fairly low scoring ones, but you know, they could have some good idea that eventually leads you to the really good stuff. So in practice, yeah, that's a good point. In practice, I don't think it would look like quite as smooth. But our assumption is that the score does give you some signal that will point you towards the right direction. Yeah, but that's a very good point. Yeah.
Perhaps one more question.
Yeah, sure. I don't know how to choose.
Oh yeah, go for it. Yeah. But make sure to repeat it for the audience.
Oh, sorry. Yeah, good point. Yeah. Yeah.
Does the LLM always generate syntactic and valid code? And what do you do with non-valid code?
Yeah,
Is it that?
That's a really good question. So the question was, does the LM always generate like syntactically valid code that you can even run? So yeah, that's a very good point. And the answer is it doesn't. Sometimes it generates code that you know doesn't even run. Sometimes it generates codes that, you know, it runs, but then it has some kind of error. And what we do right now is we just basically discard it. But I don't know if that's optimal to do, because like it might have some like really clever idea, but then there's just some like syntactical error somewhere. So it might feel wasteful to just completely discard it. But right now that's what we do. We just discard it if it doesn't run. And I think in practice, in experiments, I'd say something like 80% of code is syntactically correct and runs. So it's a relatively small fraction. But yeah, that's a good point.
Okay, we can thank the speaker. And Anup, I guess you want to.
Yeah,
we have a quick award session here for the best paper and challenge award.
These are yours.
Did you want to announce the poster session?
Yeah.
Actually, yes. What we do is like yeah, but it's not. We don't really like we don't like the reason we cost it is images of cell.
Yeah, this is the first year. That's right. Okay. Excuse me, folks. We have some stuff here.
Please take your seat for the awards presentation. Thank you.
Yeah, graphic learning is a bit easier to train and
So yeah, we are at the final session of this workshop, and we have some awards that we would like to hand over. So we have a Best Paper Award from the 3 oral talks we saw in earlier today. We have selected 1 paper for the Best Paper Award, and we have been running the Smart 101 Challenge, which I'll briefly talk about soon. And we have 2 awards for the challenge winners. So the Best Paper Award goes to this paper, Autonomous Evaluation and Refinement of Digital Agents. And GIE Penn would come over and take the award. This award is sponsored by Math Kangaroo USA, which is a organization that has been doing Olympiads since some time. So then we have this challenge award. So the Smart 101 Challenge is a challenge that we have been running since about a year, and it's actually trying to understand the abstraction, detection, and generalization abilities of large vision and language models for solving problems that kids can solve very easily. So LLMs can perhaps solve maybe a 12th grader International Math Olympiad question, but is it actually capable of solving problems that a kindergarten kid can solve? And is there a gap in their reasoning abilities? And that's something that we have been working on and trying to evaluate all the large language models, including GPT-4o and such. We have a paper coming up probably next week on this. Yeah, you can wait for the paper. But then for this particular challenge, we collected about 100 puzzles so we have this Smart 101 data set, which we released in CVPR last year. And we created a test set, which is not publicly released. And we conducted this challenge on evaluating submissions on this test set. And it has 100 questions. It's all of this children's Olympiad or children's puzzle nature. You can see here, these are questions that even kids can solve pretty easily. And the question is basically, can all these large language models able to solve these problems? And so we had about 15 participants from all over the world. And we had nearly about 15 submissions. The evaluation was, so it has 100 puzzles in the data set. And the evaluation is using something called VOSA, which is like, so you have a problem, and every problem has 5 options. So a submission has to select the correct option from these 5 options. And every question also has an associated score. So the score can be either 3 points or 4 points or 5 points, depending upon the difficulty of the problem. And half of these puzzles are only language, so you don't need to use a visual reasoning pipeline in that. And the remaining half is having vision and language reasoning requirement. So we actually did this evaluation using this metric, this VOSA metric, which is actually the accuracy weighted by the points attributed to that problem, and the average I averaged over the entire set of 100 puzzles. And so we have from the 15 submissions, we have two submissions which have very similar pose accuracies, and they are as listed here. One is from South Korea and the other is from China. And so they apparently have the same VOSA performances, and it's actually pretty low, which is surprising because they have been using all the latest large language models, except we had the requirement that they cannot really have internet search or kind of query GPT-4o during the evaluation. So there was no internet access. So whatever large language model they can package in a Docker image and submit to us, that is how we did the evaluation, so that there's we're not exploiting something beyond what is out there that they have created. So one thing is basically to note here is that the text VOSA, which is the performance on text-only puzzles. So one of them have better accuracy on the text VOSA, and the other one has the vision and language part as well. And other submissions didn't really perform that well. So we had a tie, and then all the two teams were asked to actually submit archive papers explaining their method. And then we had a review of their papers to understand which one seems better, more novel and such. And we selected one paper, one of these submissions for the challenge winner and the other one for the runner-up. So the challenge winner award goes to Jinwoo An and the team. Team's name is given here, HYUMM Lab KT. And please come over and take your award. Thank you. And the runner-up award goes to Zijian Zhang and Wei Liu. Zijian is unable to come to take the award, but somebody else there was a replacement, but I'm not sure where the person is. Well, we'll send the award to them anyways. All right. So we will have the winner talk a little bit about the approach that they have used for this. So a 5-minute talk you can give. Okay, come over, please.
It's being shared on Zoom. I don't think it's being shared.
Oh, you have to sit here. It's shared from my side. Okay.
I start all. Okay, thank you. Okay. Hi, my name is Jin An, and I'm master student at Hanyang University, South Korea. And it's great to be here, and I'm really excited to talk about our solution of the Smart 101 challenge. And during the competition, we aim the large-scale vision language models to achieve very high level of visual reasoning ability with this localized multimodal representations. So I'll talk about briefly how to extract and utilize these representations during the 5 minutes. Okay. Okay. So to start with the main problems, our problem is to solve visual linguistic puzzles like on the right side. And we all know that these puzzles composed of 8 categories, for example, like counting, math, algebra, and path tracing, etc. And these categories requires different skills and their combination. So in order to solve these puzzles, we need high level of visual reasoning ability. So To tackle this problem and with this approach, our main idea is to utilize reasoning ability of large language model. So in order to use large language model in a multimodal problem, we use language grounding, which is a well-known approach, which convert images into text token format for the LLM's input. And likewise, we also converted the input image to the text captions that capture the content of the image. So in order to obtain highly detailed text captions, we built a two-step strategy, like on the right side. First, we generate question and answer pairs about the image, and then by using these pairs, we create caption of the image. So although we use LLMs and this language grounding, we obtained a high performance rate. But moreover, we utilize the object detection-based image feature to prevent potential information loss from language grounding. And this feature gave us to capture geometric patterns may be overlooked in the captioning process. So we can see above the image, like this is composed with not the real world scenes and rather than just diagram form. So we adopt a segment anything model to obtain fine-grained visual perception. And as you can see at the right side, the feature of VIT and SAM could be extracted from the input image and then plugged into the Q-former with the caption that is pre-extracted at the before stage. So I want to explain about the overall multimodal reasoning framework as with combining the previous two methods. So starting from the left side with the given image, question, and their options, we first generate 3 sets of visual question and answering pairs. And by using this as the history, we generate actual caption of puzzles. And then we enhance the visual understanding ability with the fine-grained visual features from the VIT and SAM. And finally, the image and text embeddings are processed through the Q-former and the LLM, which is from the instructive T5 base model. And additionally, during the training phase, we utilized additional data sets to enhance understanding synthetic puzzle images. So 118,011 additional instances from the Math Vista and Science Korean and other data sets are used during the training phase. So for the experimental result on the test phase during the competition, we can see like when we independently adopt each of the methods we introduced, the model gave us the good performance on specific evaluation metrics. And with the overall combining the method, including the language grounding caption, SAM features, and training with additional data sets, we performed the best on the total WOSA. And to conclude, we focused on utilizing reasoning ability of LLM to solve the complex video linguistic puzzles and to use LLM to solve multimodal problem. We suggested 2 main approach, which is generating high detailed captions with the given images and to use object level visual representations. And through the competition, we showed that combining these ideas result in very high performance. And other training details or miscellaneous are on our archive paper. You can search with like Smart 101 solution for CVPR 2024. And our code is open on the GitHub. So send me an email for other questions or etc. Thank you for listening.
Thanks, Ejin. So that's all for today, and I hope you all enjoyed our talks and paper presentations. And so we would like to thank you all from our team for attending this ceremony of this workshop, and we'll all look forward to meeting you probably for the next episode of this workshop. And We are not concluded yet. We have a poster session in the Arch building, so please please move ahead towards the Arch building for the poster session, which will be for half an hour from which will conclude in half an hour, but it should be set up now. So please go ahead going there. That's all for today, and thank you so much. Bye.
In the Zoom call?
Zoom call. So this one we did. This is the
No.
No, they got the.
They're the winner. You're the second.
Okay.
Oh, yeah. Sure. This one. They're the winner.
This is you. Yeah, we have to.
I think there are two, right?
Oh, wait, what's behind that one?
Oh, it's the same. Yeah, it's the same one.
Oh, behind that, is that 2 pages or one?
This one.
Okay, so thick.
Oh, yeah. So we'll
Congratulations.
Tim,
Yeah,
you want
no,
to
it
come
was
this
two.
side?
Yeah, you're right. Yes.
Tim, you want to come this side?
Another picture?
Yeah. Moitreya, you want to come this side as well? Yeah. Oh, yeah, sure. Moitreya, you have to come this side.
What's the picture of?
With all of us together. Emily.
No, organizer.
Guitar is. Great, thanks so much. Emily, you have to come. Oh, you can just take one more picture. Peter, I need to see.
Peter left.
Moitreya? Oh, you want to take a picture? It's the same as my camera.
He's
Fine.
got it.
We need one.
Yeah, he's got it. There we go.
Thank you very much.
Thanks
so much. And thanks for organizing. It's a really cool workshop.
Yeah.
Thank you.
I think I read your work on equivariant neural rendering 2 years ago. I didn't realize it was you.
It's so long ago, yeah. Actually,